Good afternoon. Welcome to CL Creative Space. We'll start our festivities in a few minutes. One, two, testing. 1, 2, 3. One, two. 3.
right, let's get started. We're live with Transformers at Work 2024 here from beautiful Berkeley, California. My name is Jakub Zavrel, and with me is
Dinos. Hi, everyone. I'm a research engineer at Zeta Alpha. Welcome to the 5th edition of the Trends in AI conference, workshop, however you want to call it. So, yeah, this is a very special moment for us because usually we host this in Amsterdam. And since it's our 5th anniversary, also as a company, we said, why not? Let's spread our wings and go to Berkeley.
All right, so let's get started. We're also broadcasting this live on Zoom for the online participants, and as an experiment, also simultaneously on YouTube, Twitter, and
LinkedIn.
And LinkedIn. So what could go wrong for the first time? We would love you to, take pictures, ask questions, use the hashtag Transformers at Work, TAW 2024 on any of these media. So we're here essentially to celebrate the transformer in its many forms. One of them being the algorithm. How did it start?
Well, there was this great paper from a bunch of researchers at Google, then researchers at Google.
2017, right?
Yeah.
Attention is all you need. That's really what got this whole revolution rolling. An amazingly flexible and scalable algorithm that really changed the way deep learning works, right? Before then, it was a bunch of black magic, and now we could really start to build these very powerful models.
Well, I would still argue that it's still kind of black magic, but at least scaling and all these kinds of things have picked up from then.
Back then, only these 6 people, sorry, 7 people. No, I'm bad at counting, like LLMs, 8 people. They knew how it works. They all left. They all left Google. And now some of them are coming back. That's very exciting after becoming billionaires. So it was not a bad idea. This paper. Can we get the slides? Yeah. Our journey as Zeta Alpha started around the time that the transformer was turned into BERT. Who here remembers BERT? Everybody almost, right? So yeah, BERT really got, so I've been in natural language processing and machine learning for about 30 years. BERT was the first sort of universal NLP algorithm. And everybody at ACL and EMNLP was like, okay, let's put everything aside. This is the new thing. And very quickly, we started seeing these breakthroughs. So we started Zeta Alpha around that time, a little bit after BERT was published, 2019. And we thought this is going to really cause a revolution in the way people deal with knowledge in companies. We started building. Then GPT-2 came, and that was really exciting. It was still kind of flaky, right? But we started building our platform, and
well, GPT-2 had kind of the same headlines that we have today. It's gonna end the world. It's gonna be very dangerous.
Very dangerous. Don't release it. Yeah. The transformer started in with text in natural language processing, and very quickly people realized as long as you can tokenize your data streams, you can use the transformer and all its scalability and representational power with the attention mechanism. So very quickly, the computer vision community adopted it. It was adopted for speech, for basically every modality. Very recently, Andrej Karpathy tweeted, yeah, this large language model name that's become so mainstream now is really a misnomer. It's really kind of a universal token predictor. And here you see with some analysis that we have done on a data set of basically all the AI and data science research papers over the years. And you see how the orange graph here, which represents the text use of the transformer, is getting smaller and smaller. Other modalities, and especially multimodal here, is growing, and now it's kind of popular across all modalities. So the modern LLM is really no language model. It's a universal token predictor, which treats all the modalities as tokens and can generate and predict across all of them. And that's led really to this enormous amount of excitement and investment also. I'm not sure what the exact number is, but these are just the headlines of last month. So we see some very big names. What's your favorite one?
I mean, it has to be the 1 billion seed round from Ilya Sutskever's new.
That's a pretty big seed round, yeah.
For a company that swears that they'll do no product, just research.
Yeah, we also see here some of the headlines about the modern rage, which is the sort of semi-closed acqui-hire, like character AI, where the people actually went back to one of the original attention is all you need authors went back to Google. We see lots of different startups being funded. One of them also Contextual AI, founded by Douwe Kiela, who's going to be speaking here in a later session today. So where is all that money going? Well, most of it is going to
NVIDIA.
NVIDIA, exactly. Who here is a customer of NVIDIA in one way or the other? Almost not everybody. So what are you using? We'd be curious to know. There are alternatives, of course, but we just saw in the headlines that NVIDIA had this another record quarter, I think more than doubling the quarterly revenue, super high profit margins. Interesting piece of news in that release was that actually around half of the revenue is coming from 4 customers. If you're a startup and you want to get investment, that's a red flag for the investors. But there's also a lot of competition growing. Interesting fact is, of course, that the NVIDIA hardware is highly optimized for the transformer. So on very few other accelerators, you get such a high performance on transformer models. The H100 is fully optimized for that, right? But there are alternatives coming. Etched, some South Korean startups. Grok has got quite a lot of attention. And Cerebras just very recently announced the fastest inference service for Llama 3.1. And we're very lucky to have Natalia. Where are you? There in the back from Cerebras, also going to talk to us. And of course, we have also NVIDIA represented with Rama Akkiraju in the first slot after this introduction. So what's going on? Well, there's new releases all the time. I think everybody's trying to figure out right now what Strawberry or O1 can exactly do. A lot of advances in reasoning, especially, right?
Yeah, so this new model from OpenAI claims this does reasoning better. It takes time to think. It thinks in a language that is not shown to the user, but the user kind of pays for it. But we kind of trust them because also the benchmarks are pretty good on math tasks and general coding capabilities.
And so basically, what
is the secret?
OpenAI, we don't know exactly how it works, right? There are a couple of papers related to it. But one of the interesting things in terms of scaling laws is that the scaling laws have been kind of extended to inference time compute, which basically means that it's no longer the OpenAI investors who are paying for the compute, but
also the clients,
all of us. Well, there are some publications which indicate a little bit how it works in terms of its reasoning chain of thought, plus some reinforcement learning, and multiple models playing back and forth with each other. So it's really become kind of a system for reasoning rather than a language model, right? So the other trend that we're seeing is really multimodal. So this is also from last week, right?
Yeah, probably the last 10 days or so.
Yeah,
We have had
So what do we see here?
we've had Qwen2 VL, which is an open source permissively licensed vision language model. And yeah, from the benchmarks, it seems it's quite competitive with proprietary models like GPT-4o and
So
Sonnet.
even on multimodal, open source models are catching up. We see small but high quality models like Phi. I think this is also multimodal, right? The Vision Instruct Phi being very competitive. And finally, we're from Europe, so we're proud that also Mistral plays along with the big guys. And last week they released this Pixtral multimodal model. So I think another trend that we're seeing is that single language model applications cannot do everything, and we're seeing orchestration and chaining or tying together of many different prompted models with different workflows, and basically the construction of agents. So basically this week we had Dreamforce here in town. I think Salesforce with Agentforce is betting their whole company on the agent concept. So is Slack, well, that's also Salesforce. And Microsoft introduced a whole new generation of the Copilot thing, which also bets very big on kind of low-code availability of agents in the enterprise. And there's a ton of very cool and hip startups being launched around agents. For one of the coolest ones is Multion here in San Francisco, and we're super lucky to have Julia over there as a speaker in this conference, talking about evaluation of agents. So this whole concept of transformer models or large language models being useful for the enterprise kind of started with this tying large language models to tool use, right? There was this paper called Tool Farmer, which kind of started that.
Yeah, and I think we see kind of how a language model can use other things that are just not a generative model creating stuff, but calling existing services like APIs or
very simple
files.
concept: tokenize the output and make tokens for actions, and then it evolves into actual products with, for example, function calling that both OpenAI and Anthropic are offering. And when you talk about transformers at work, so transformers for workplace use in the enterprise, this is not surprising that we need tools and agents, because if you have a user who has a question and is going to just ask it to the pre-trained knowledge of the LLM, it might get a good answer if it was in the training data, but if it wasn't, it's very unlikely to be correct. So we got the whole world worried about hallucinations or incorrect answers. In NLP, we're kind of used to that, but we're seeing enormous adoption. So everybody wants to use ChatGPT-like products in their daily life, right? For summarizing things, translating things, brainstorming, all these kind of very handy productivity applications. But if it doesn't know your own data, it's going to be very complicated, right? So even in the GPT product, the consumer product and the enterprise product, you need to feed it your own data in the prompt somehow. So there's this kind of little bit practical thing of uploading your files. But it doesn't really give it the whole knowledge of the entire organization. But it's quite useful. ChatGPT Enterprise is seeing a very large adoption. Here, for example, at Klarna, they are super excited about it. But why? Well, if your boss is excited about introducing ChatGPT at scale, it doesn't always have beneficial motives for the workforce. So Klarna actually hopes to get rid of most of their employees. So tool use is essential, enabling LLMs to be able to deal with your own information, and the pattern which has emerged as the dominant sort of architecture for that is retrieval augmented generation. A lot of the talks today are going to be about retrieval augmented generation. Actually, we could have called this workshop, I don't know,
Transformers for RAG.
RAG at work, RAG fest, RAG time. So I think you guys are familiar with the pattern. Basically, instead of directly answering the question, you also dispatch that question to a search engine. And because we're dealing with natural language questions, this is a complicated search task where you need to map the semantics of the question to the semantics of answers. They don't really have the same kind of keywords. So that's why we've seen these kind of vector search or neural search or embeddings-based search become really popular. So we have, go back to that slide. We have a lot of talks about RAG in the workshop. One of the authors of the original retrieval augmented generation paper is Douwe Kiela from Contextual AI, who will be here. But our first opening talk will be by Rama Akkiraju about how actually RAG can be implemented in a very complex enterprise IT setting. I think that's a very cool talk to watch out for. So we've seen the emergence of a lot of frameworks. I think LangChain and Llama Index have kind of swept at least the Bay Area scene and the world in building quick prototypes. There's other frameworks, for example, in Europe, Haystack by DeepSet is quite popular. And one really cool framework that has recently come out of Stanford University and emerged as a kind of different paradigm of building these kind of RAG and agent-like applications is DSPy. And we have on the program one of the contributors and members of that research group, Michael Ryan in the back there, talking to us about prompt optimization in DSPy. So these frameworks, of course, make it really easy. Some blogs argue that you can build your RAG applications in 5 lines of code. Fernando, my CTO, says this is not 5 lines code, this is 3 lines of code, but it kind of works, I guess. But there's a lot of complexity that's that is not dealt with here. In practice, so we build a lot of these RAG systems. The more typical RAG pipeline looks quite more like an agentic systems with different flows being strung together, different search strategies like keywords and neural search and re-rankers and rank fusion being integrated. So we'll be talking about those kind of recipes as well. At the same time, so basically it meant that people in AI have started to rediscover the field of information retrieval. There's been about 5 decades of work in information retrieval, talking about search relevance. And yeah, that's really becoming a new key factor in the success of these RAG systems. At the same time, information retrieval itself is being disrupted by large language models. We were at SIG-IR, the largest information retrieval conference earlier this year in DC in July, and this one. And basically, yeah, most of the sessions were kind of self-help sessions. How do information retrieval researchers deal with this change that LLMs are bringing? And one of the best talks in SIG-IR was by Zhuyun from Google Deepmind, who's here with us and will be giving the closing keynote. And she has personally pioneered a lot of these techniques and caused this disruption, so to say. Transformers at work. So information retrieval is being disrupted by LLMs, but recently we see that it's even being disrupted by computer vision folks. So there's this paper that you really should check out if you haven't yet, called Call Pali by a group of French researchers, which basically, Dinos, what does it kind of do?
Well, it takes the idea from Colbert, which is based on multi-vector retrieval and this paradigm of late interaction. So you tokenize your input, your documents, your queries, and you store the embeddings on a token basis, and then you use an index that supports finding basically the maximum similarity between the query and the whole document tokens. So they do the same with images. So you just split your image into patches, and you can just search the document which has the golden patch or answer to the question based on visual information.
So basically, Pali marries Colbert and Polygemma, which is a vision language model from Google, and it kind of eliminates the whole classical information retrieval or natural language processing pipeline. You basically take bitmaps of the pages of your documents and feed them through computer vision input of a multimodal model, and then you don't do any chunking, any sort of PDF to text conversion. You don't do all the sort of named entity and other crazy things that people used to do in the past, reducing the indexing time from roughly 7 seconds for a full PDF pipeline to less than half a second, and also giving really good results. So here you see the benchmark results from that paper. Not sure you can read that on the screen, but the bottom line is Pali and basically beats both clip-based models, text-based models, and other approaches by a huge margin on a benchmark which is kind of questions about figures and tables mainly, but also does about equal on text-based tasks. So who knows? This is a big disruption for IR, I think. Check it out, Pali. So transformers at work. So how is the adoption of AI in companies? Well, it's going very rapidly. So here's some research from G2, the company which gathers a large amount of software reviews and software usage statistics. AI is the fastest growing software category, growing 38% over the last year. Some subcategories like AI image generators are even growing faster. I wouldn't know if that's like fully enterprise or business to business use or more personal productivity, but yeah, it's going very well. Deloitte just in August released this very nice research piece where they interviewed a large amount of IT executives from large companies. The State of Generative AI in Enterprise report. And yeah, they see that 67%, so 2/3 of the organizations, based on their initial experiments, are increasing investments in generative AI solutions, given the value that they're already experiencing. So where is that value? Well, a lot of it is in efficiency and productivity, right? It's easier to start with a sheet of paper where you just need to correct a few things than an empty page. But also encourages innovation, improves existing products and services, and increases the quality of work. But it's not only rosy. We also see that less than 1/3 of these Gen AI experiments are actually making it into production. And in this workshop, we also want to explore kind of what these bottlenecks are. And we have in the first session, Raza Habib, who's going to be talking about the patterns and anti-patterns that lead to this kind of statistics. Some of the concerns are not so much about technology, maybe, well, a little bit, using sensitive data or data privacy issues, which obviously those 5 lines of codes with the LangChain are not going to solve, where you need a more mature IT infrastructure around the whole thing. And it's more than technology, right? So we're in this workshop, we're techies, so we're going to be talking mostly about sort of this side of the screen, about algorithms and data sets and methodologies. Evaluation maybe a little bit, but there's a lot more to it. Talent, building up the right teams, processes and strategy, and up to like compliance and legal and ethical concerns. So we just want to let you know that we see the whole picture, but we're working on mostly on the tech side. So those of you who haven't heard about Zeta Alpha, we are a company from Amsterdam. We just celebrated our fifth anniversary last week. And we've been working on this platform, AI platform for connecting people and knowledge for the last 5 years. Since the end of last year, we're frequently visiting here in the San Francisco Bay Area. And basically our mission is to help knowledge-intensive companies in domains like chemistry, pharma, electronics, high-tech manufacturing, to turn their proprietary internal expertise, which is not in all cases public, into generative AI capabilities for their next business innovation transition. Won't be doing a demo now of the product. In the breaks, we'll have demos over there in the corner. But basically it allows you to search and ask questions and have dialogue with your own proprietary data, chat with documents across languages, across modalities, chat with collections, and evolving into this kind of assistant with your work over a longer time. My colleague and CDO, Fernando, will be talking more about our architecture. So basically, it's a multi-tenant configurable services cluster with pipeline for connecting to different data sources and respecting access rights and all that, and then providing search and also agent capabilities on top of that. A couple of things that we do is especially customize for these complex knowledge-intensive domains. We've developed and open sourced two approaches. One is in-parse, which allows us to fine-tune, especially the retrieval part models of RAG, to using synthetic data. And the other is evaluation. I think both Raza and Julia and many others will also touch upon the issue of evaluation. And we've open sourced this framework called the RAG-ELO, which implements LLM as a judge. We implement this for companies like BASF, where we have built a generative AI solution for the research scientists. Research scientists care a lot about retrieval quality. If you give them an answer which is kind of referencing the wrong compound or the same process but at a different temperature, they will laugh at you. And this, they also have very little time to evaluate results, which led to this development of this LLM as a judge framework called RAG-ELO. In the graph, you can actually see the iterative evolution of the retrieval quality over a series of experiments. And I think you will understand that the difference between precision at 10 of 30% and 80% is quite a game changer for RAG. Given the time, I won't go into all of these use cases, but we work with Deloitte on regulatory documents, seeing similar effects of fine-tuning there, and allowing financial professionals to get answers to questions with references to legislation. We work with companies in industrial automation like Festo, where we're building whole generative AI kind of factories to develop many different use cases. All in the same framework. And this is an interesting example of a completely different thing, matching jobs and people, which I used to do in a former life, where we're fine-tuning models and also seeing much better accuracy. So I will close this introduction with some announcements that we want to make. The first one is that we're really proud to be partners with Microsoft. And recently we have put our neural discovery platform in the Microsoft Azure Marketplace, making it easier to buy for large corporates. And we also want to go where people are in their work, which is not going to log into a new platform, but they're actually, of course, in Teams and in Copilot. And so we make Zeta Alpha also accessible through Teams and Copilot as a plugin. All right, we're also proud to announce our first open embeddings model, Zeta Alpha E5 Mistral, which we have made fully open and also documented the whole process, how you can build a model like that too. And we're quite proud to have landed it in the top 10 of the well-known MTAP retrieval benchmark.
If anyone is curious, feel free to find me at the break and I'll tell you all about it. I'll also made a lot of the process documented and available for everyone.
Yeah, the code is available. And we have a whole bunch of product updates, which are maybe not that interesting for you, but in Fernando's talk, we'll be introducing the new Zeta Alpha RAG Agents SDK, which basically allows you to bring your own LLM agents and deploy them on top of the secure enterprise search infrastructure. We have a bunch of good improvements to our search and ingestion APIs, new documentation, and improvements to the chat UI, which you can see in the demo later, and improvements to our Reglo open source evaluation framework. So we're ready to start the rest of the program. Thanks for coming here live or online, joining us online on one of the streaming channels. If everything went correctly, you received a bag with a little program booklet. We're probably already running a little bit out of schedule. You see there the Wi-Fi code and the hashtag for the conference, and you have the program. So we're going to have the first session now with 3 talks. The format is 20 minutes talk plus 5 minutes questions from the audience. Then at around 2:45, we're going to have a first coffee break, then the second session, and then another coffee break, last session, and a panel, which will end at 6. And it's not over then. We actually have a band in the evening who's going to be playing here, local talent here from Berkeley, California, Honey Knuckles. We're going to start around 7. We have food and drinks, so stick around and enjoy the beautiful evening. And if you're going to be tweeting or posting on social media about the event, use the hashtag TAW2024. And yeah, this is the band. And with that, I want to close this opening and open the first session.
Yeah, thank you everyone for the introduction. So yeah, based on the time that we have, I think we should probably move the coffee break to be at 3 to 3:15. And yeah, let me bring up my cheat sheet for the first talk. Our first speaker is Rama Akkiraju. She works at NVIDIA and currently is a vice president of AI for IT, where she leads AI and ML initiatives for enterprise use cases. So you can see how this is very relevant for our workshop today. She has had a long, successful career previously at IBM as an IBM Fellow, Master Inventor Academy member, while also serving as a CTO of IBM Watch on AI operations product. So, I mean, the accolades go on, but what's relevant for us today is that she will be sharing some facts, and what that means you'll find out in a bit, about how to build these Gen AI chatbots, including tips, tricks, and best practices from 3 case studies in different domains. So the floor is yours, Rama.
Give a warm applause for Rama.
Good afternoon, everybody. I'll start as soon as my slides are up. But thank you, Jacob and Zeta Alpha, for inviting me to this. As I was introduced, I will share with you some of the lessons learned and the work that we've been doing at NVIDIA. My mission at NVIDIA is to transform NVIDIA's own enterprise with AI. And as part of that, I look at all of our business processes, employee productivity, IT, supply chain, sales, marketing, and so on, and identify opportunities for transformation with AI and generative AI, and also build platforms that all of these business functions and folks in these business functions can use to quickly accelerate the AI transformation. So across in terms of the use cases, as I said, we are looking across all of the different business functions. Today, I'll spend some time talking about some of the use cases only. Obviously, I cannot go into all of them, but I'll just pick one or two from each one of these business domains to talk through, just give you a flavor of what we are doing. In the case of customer support, of course, the entire generative AI revolution is starting with chatbots for customer support as the primary use case. Even pre-ChatGPT, that's been the #1 use case in the industry. So, of course, with ChatGPT, it makes it all the more relevant and useful to tackle that use case first. So we have been building chatbots internally with generative AI RAG-based solutions. So I'll talk about that today as the primary one. But in IT, supply chain domains, we have a number of projects. In IT, for example, we are working on building chatbots for SREs, the site reliability engineers, to help them quickly detect incidents, diagnose them, resolve them, and address the incidents faster. And in engineering, of course, code assistance tools, code review tools, and unit test generation tools, and all these are all things, some of the things that we are working on within the company. And in supply chain, quickly enabling the what-if scenario analysis of various supply chain planning activities that you do, demand-supply matching, how much demand to allocate to supply to customers, and how much supply to allocate to customers, and so on. So all of these planners interacting with it in natural language and enabling those kinds of use cases possible, and a slew of others in sales, supply chain, HR, and all of that. So let me get to the meat of the talk today. If I have to summarize our learnings, I'll say the following way. These are the facts about building generative AI solutions in the enterprise. And facts, pun intended, is an acronym that I've coined up to really talk about these 5 things that we learned. Each one of these letters in the word fact stands for something. F is for freshness, A is for architectures and agents, C is for cost, T is for testing, S is for security. These are all the things attributes are things that we had to really optimize for in order to deploy our Gen AI solutions. So I'll talk about each one of them in detail. Let's go through the F for freshness. And I'll talk about it in the context of customer support chatbots as we are building it. So pre-Gen AI era, like everybody else, we also had a chatbot at NVIDIA. It was built with pre-Gen AI, but it BERT, and there is intent detection. When user asks a query, you detect the intent, and based on that, you route the query accordingly. You do information retrieval, retrieve a relevant knowledge article. Same thing it was doing, but our intent detection was pretty pre-Gen AI world, right, where you have to teach it with a lot of examples, and it wasn't that great at the BERT technology or whatever we were using. Not that great at really understanding the intents more natively and naturally. And this is how our chatbot architecture looked like. And the one on the right hand side really is hard to see, but it's an example of how to address VPN related questions. These are the dialogue trees that we had to build. And imagine how fragile and how hard it is to manage and maintain them in the enterprise. And if you, for example, change your VPN process to something else, you have to go redo all of these dialogue flows and then rebuild the intents and so on. So yeah, we all know that kind of a chatbot maintaining those kinds of dialogue flows is just untenable in an enterprise. And so fast forward to post ChatGPT, we've built a retrieval augmented generation based solution. A lot of learnings I'll take you through, but this has been the year of deployment. If last year was the year of exploration and proofs of concepts. So a simple LLM flow looks like this. Obviously, this is not going to cut it for building a chatbot. I'll talk through from an example perspective 3 of the chatbots that we built as to what it takes to really build a real deployable version. We've built chatbots for answering questions, IT help and HR benefits types of questions in the enterprise. We built chatbots that can answer financial earnings types of questions, and for salespeople to summarize their long trip reports that they write from multiple people and so on. A year into all of the POCs, we have many of these bots. Actually, all 3 of them are in production. And here is how it looks. I don't know if you can read it. It's probably not that readable from that far, but I'll kind of just give you a flavor for some of them. You can ask questions about how much does NVIDIA contribute to healthcare savings account? And it gives you not only the relevant article citations, but the quick summary of what contribution that is. You can ask about company policies, can I bring dogs to work? And can I park my car overnight in Santa Clara headquarters building? Or you can ask about I'm having problems with my VPN, how do I do it? You can take a screenshot of the problem you're having, just upload it, and it will do OCR detection, and from that understand the problem and automatically find and retrieve the documents. You can ask about, hey, what did, I was at Dreamforce last week too, checking out all those agent forces. What did Jensen and Mark Benioff talk about at that conference? And it goes and looks at the blog posts that were released on NVIDIA's site and summarizes that and so on. So all kinds of this. We can also ask about NVIDIA's revenues. What are data center revenues for 2024 or for the last 3 quarters? It's a complex question that needs to be decomposed into what are the last 3 quarters? Oh, the fiscal quarters, can translate them into 3 different quarters, decompose the query, run it as 3 different queries to do that. In all of this complex query decomposition, query rewriting, query rephrasal, chunking, re-ranking with retrieval, all of those things, we built pipelines and platforms, and now all those bots are in production. So summarizing the learnings, where are my charts? Yeah, so here is a typical retrieval augmented generation pipeline. Looks like user asks a query. There is you take the user question, rephrase the query. In a simple setup, you probably won't even rephrase the query. You just send it to a prompt. All the enterprise data, which is you see on the right side. Let's say you indexed it into a vector database, and you did hopefully all the right things in terms of metadata and enrichment, the right kind of chunking strategy, pick the right embedding model and all of that, and put it all in. And you would think that it would retrieve the right chunks, and then you send the chunks to an LLM and you summarize and you get the answer. You would think this would work. The answer is no, it won't work. There are 15 different control points in a RAG pipeline that we've identified and we've written a paper about, and it's available in archive. And each one of these control points really kind of has significant impact on the quality of the results that you generate. User's query, first of all, needs to be rewritten, rephrased, and may have to be rephrased in multiple ways depending on the kind of retrieval system you're using. Jacob, you were talking about using, using the good old information retrieval solutions, and they're getting a makeover for sure with vector databases. But the way to get most relevant chunks from them may not be by sending a natural language query. That won't work for probably, depending on the system that you're using. You may have to break it down into more keyword-based kind of searches, but you may also have to rephrase the query. So for example, when I ask, what are NVIDIA's data center revenues for the last 3 quarters? There is no document that has data center revenues for the last 3 quarters. If you send that to an information retrieval system, you won't get any chunks back at all. You have to break it down into, data center revenues for fiscal FY25 Q2. Maybe there will be an article for that. And you have to understand the last 3 quarters as a date and really transform that natural language into a date filter and break it down into these 3 different queries. And unless you do all that pre-processing of a query beforehand and actually give the right kind of the query to the retriever that is likely to have hits, you won't fetch anything. So query rewriting has a significant impact on what the relevancy of the chunks that you end up retrieving. And once you get the retrieval, from the retrieval, the chunks, even there is a lot of nuances in terms of the chunk size and what kind of embedding model you're using and all of that. So assuming that you've got all of those things right, there are company-specific guardrails. If it is a question about somebody's asking, is John Doe on performance improvement plan? You don't want to answer those kind of questions. Even first of all, those kind of documents should not be public in an enterprise, but people do make mistakes. Sometimes sensitive documents are exposed in the enterprise, but chatbots cannot reveal it. So you have to guardrail it. So there is a lot of guardrails that you have to bake into it to say, don't answer these types of sensitive questions. HR folks will have certain kinds of restrictions. IT team may have certain kind of things that need to be guardrailed for. And finance teams will have certain kinds of guardrails. So when you're building a chatbot for the enterprise, you have to understand each subdomain's requirements and their guardrails, and you have to incorporate those guardrails, which means that's another LLM call. And then, of course, when you get the chunks back, you have to re-rank the chunks appropriately before you can send it to an LLM. Which LLM to pick also makes a significant difference. So at each step of the way, really, it's like it's as much an art as it is a science. You have to have the right kind of tools that will help you automate all of these different control points in a RAG. So the summary of freshness, F for freshness in facts, is that yes, you have to use retrieval augmented generation to serve up enterprise data, because foundational models don't understand the enterprise data. So you end up ingesting that into your vector databases. So you can actually use the foundational models for final summarization, but you retrieve the right chunks. But the art of getting that whole RAG pipeline, the retrieval augmented generation pipeline, right, is non-trivial. So there is a lot more work that will emerge, I'm sure, as in platforms and other things in the coming few years, months, decades. I guess in the world of LLM, it's days. But yeah, there is a lot to get right there. So here are some examples. So these are a summary of the learnings, right? I mean, I talked about this, whether to customize LLMs or not. Should I fine tune the LLMs or not? And you end up in that RAG pipeline. There are about 7 or so LLM calls you end up making. And each one requires its own continuous improvement plan as well. When users give feedback that your answer is wrong, is it because the retrieval is wrong? Is it because the rephrasing is wrong? Is it because the re-ranking is wrong? Is it because the LLM response is wrong? Is it because the guardrail is wrong? Each one of is an LLM call. You have to be able to attribute it back to the corresponding LLM and actually build the corresponding improvement cycles. That's the post deployment. But even before deployment, you have decisions to make on whether to customize the models or not. So there are a lot of learnings there. So next, moving on to the second one, talking about architectures. We are moving at a pace that's unprecedented. So LLM models, new models come on as leaders on the board every day. New retrieval augmented systems are coming on the board every day. As you build a platform for building any kind of generative AI solutions, if we don't do a good job of actually building a very adaptable, flexible architecture, we'll end up with something that's outdated even before you go to production. So these architectures have to enable you to really, and I talked about these problems, have to enable you to change LLMs fast, be able to experiment with prompt fast, be able to do the whole evaluation pipeline and regression testing with your data set fast, and be able to even swap out your retriever fast. And at each step of the way, what is the right LLM? Do I pick a smaller model or a bigger model? Which one will give what trade-offs? All of these things you have to be able to keep changing and experimenting, but the architecture has to allow you for that. And the entire evaluation framework and testing framework has to enable you to do that fast, to iterate fast during development and in production once you go post-production. Otherwise, it just becomes, you just have a static system that gets stale and outdated very fast. So we've built such a platform internally, and we have a low-code, no-code kind of a thing as well, where people can just look at various different build LLM flows and play around with LLMs and retrievals and all of that and test them there before deploying. There are many complex RAG patterns that still need to be addressed, and here is a flavor of some of them. You may have to summarize across very large number of documents. That is not a natural case for retrieval in the enterprise. And you may have to do summaries of summaries of summaries, and like sort of like MapReduce. LangChain types of frameworks allow you to do that. And we had a number of use cases that we solved that had that kind of a pattern. We had the patterns that I gave as examples: complex query decomposition. People may ask multi-turn questions or multi-part questions. You have to understand them and decompose them. And people may ask questions from multiple domains, and you may have to go orchestrate with different agents to call different API calls to get the right kind of response from each subdomain agents. So we have built several examples of those. These are all examples from our productions where we built with aggregative summaries, where people ask, summarize me all the emails corresponding to such and such topic. And all of that data may be in your RAG, but you still have to fetch them and in chunks at a time, because the context length does not allow you to get everything and summarize across all of them. And you don't want to miss anything, but just by doing sampling. So we end up implementing MapReduce kind of things. And sometimes there are examples where they say, you know what, summarize across all of them, but the ones that are sent by emails or summaries that are sent by the account executive should carry more weight. So how do you know who are the account executives? So, and how do you give more weight to them? How do you guide retrieval augmented generation to give more weight to those chunks and prioritize them? You need a knowledge graph for that. So it's a graph RAG type of a setup where you have to kind of feed that some of that information to the system and the information about who the people are and such. So we implemented those. I think I've already talked about this, breaking up data center revenues from last 3 quarters as a query into this multi-part decomposition. And that's an example of that. All of these things have to happen beforehand. And eventually, we ended up implementing an agent and this agentic architecture, which allows you to orchestrate all of these different kinds of subdomain experts, bots that we've built, because we wanted to unify the experience for NVIDIA employees. We don't want them to have to go and remember, oh, I have to go to that bot for asking IT question, I have to go to this bot for asking HR question, and so on. There is one, we envision one digital virtual assistant for each employee that understands them and their context, and they can ask any kind of question, and that's embedded as a co-pilot into all of the applications that they're using. And it's there as an assistant, and it has all the context, and it's able to go to whichever domain expert bot to answer the question. And for that, you have to really understand the intent of the user and classify that intent correctly to route it accordingly. And that's another LLM that sits in front of all of these things. That's one that we built. So that's so our journey has been, you'd start out by saying, okay, LLMs are important things. Okay, well, yes, the LLMs are important, but they're not the whole solution. You need good retrieval augmented generation solution to really work with the data in the enterprise. Yes, but RAGs themselves don't really do much unless you optimize it for all these control points. But you still need agents to really solve the problem for the enterprise in the end, because it's not just about retrieving information and summarizing. It's about really solving the problem for the user, which means you have to integrate all of these systems with different enterprise APIs for task fulfillment, task automation. Because in the end, it's not very helpful for me to just say, oh, if you want to get Microsoft Copilot license, here is a knowledge article that takes you, you click there, that takes you to where, how you have to fill in a form to get it. Now, you didn't really help reduce the problem for the user, right? Of course, the chatbot gave useful information. Instead of links, it gave the summary. But wouldn't it be nice if you actually, got the job done for the user right there with all the context? That's where agents come in, and you integrate the agents and the API with the agents, the APIs and the LLM solution, so that you automate the whole thing. And so our journey kind of captured all of that. It's the rise of the LLMs to the rise of the vector databases to capturing the rise of knowledge graph and context to now to agentic architectures to really solve the problem for the enterprise. I'll say a word or two about the other things. So far I talked about F for freshness, A for architectures and agents. Now C for costs. As you deploy generative AI solutions in the enterprise, costs could run into millions of dollars if you're using the open commercial ones. So you have to be really kind of careful in deciding what LLMs to use where, and whether smaller LLMs or fine-tuning version of LLMs will do the job for you. Otherwise, the ROI just may not work out. I report to the CIO, and first thing the CIO asks as I'm building all of this is, what is the ROI? And if I say, oh, let's deploy this chatbot, it will cost us, $150 million per year across all the employees in the company. How many users will ask this question? How much productivity gains would I get? Where is the ROI would be the question that CIOs would ask. And so really have to, the excitement wears off when the POCs wear off to go to production. Reality hits in that business outcomes have to really work out. Otherwise, it makes no sense. So a lot of trade-offs there. Smaller models, fine-tuning the models, whether you use you host them internally or on cloud. These are all decisions one has to make, and we've done some experiments to show that smaller models that are fine-tuned will work just fine for certain domains. They may be more cost optimal. And so you have to consider those trade-offs. And there are latency trade-offs too. You can't have a chatbot sitting there going for 15 seconds to give an answer. It's not so very optimal. So smaller models tend to be faster. So how do you, optimize the whole pipeline for smaller models? We've done a number of experiments that to show the smaller models actually work better. And those are some of the examples. Sorry, I'm kind of rushing through. Now I'll talk about testing a little bit. So I talked about freshness, F. I talked about architectures, A, C for costs, T for testing. Account for good amount of time for testing. LLMs generate natural language responses. It's very hard to automatically evaluate them. Yes, we use LLM as a judge, LLM as a jury. We use all kinds of automated pipelines, RAGOps, and full automations to the extent possible. But nothing beats human actually evaluating them before you take to production. And that's a time-consuming process. So creating good data sets, really making sure that all stakeholders are on board with those good data sets, and then you finally are able to evaluate and report accuracy numbers on that. And internally, you have to know how good is your retrieval, re-ranking, relevancy, and all of those things, hallucination rates and consistency rates, so many metrics need to be measured before you make production readiness decisions. And the test cycles tend to be very long. And unless we really optimize and automate, development cycles can be very long, and business leaders could be sitting getting frustrated. Last but not least, I'll talk about security. It is one of the most important aspects in the enterprise. These are very powerful tools we are now deploying. Companies did not have these kind of powerful search tools and summarization tools before. Now they are able to, when you ingest all kinds of enterprise data, all of this data is available for people to find and make use of. But in doing so, it also exposes the incorrect access control permissions on documents problems. Because every enterprise has this problem where some people not so purposefully, but end up having incorrect access control permissions on sensitive documents. And before, our search was not so great, so you could say, well, we kind of had a sense of security by obscurity. You no longer can hide under that veil. These systems will now suddenly find and expose all of that if you don't properly go fix that. So we had gone through this experience where we were ready in a very quick short order of time with our deployments, but we couldn't go to production because our security team found that sensitive documents may have to be protected first before we can go to production, and rightly so. So we then kind of kicked off security, enterprise security projects where we use LLMs again to classify the documents and sensitivity with the right kind of sensitivity labels, and have the entire process of going through and asking the owners of the data to fix the permissions properly before we ingest that document back again. So a lot of enterprise content may be out of bounds for Gen AI solutions for these kinds of reasons, unless you properly address that in the enterprise. So that's security. And we've a number of learnings from that. Each of this would be a talk in itself. So there you go. I'll summarize it by saying facts. These are all the examples. Summarize it by saying facts. Freshness with retrieval augmented generation, but lots of control points. I talked about several of them. Still an art, and requires a lot of tools, which will be emerging, I'm sure, in the coming time in the field. A for architectures, build flexible architectures and make sure that you have agentic architectures there. Cost optimization is a critical part of it if you want to deploy solutions that actually make sense from an ROI perspective. So look for small versus medium, big, and fine-tuning options. Ensure enough time for testing. Don't short circuit that. And if you don't build automation, then your development cycles will be very, very long. So you need that automation. And finally, don't miss out on security. You may do a great job, but if you don't address the enterprise document security, the projects may not go to production. And that may be one of the reasons why only 30% of the POCs are going to production and rest of them are still staying. So that's it, folks. That's our learnings. I hope this is helpful. Thank you.
Thank you, Rama. This is
Do we have time for
really
questions?
Good, yeah. So really good presentation. I hope everyone enjoyed. So we have a few minutes for questions. So everyone in the room, you can raise your hand and I'll get to you. And also online, you can use the chat or Q&A feature to ask a question. Yes? I'll bring you the mic.
It's a very good topic. So my question, NVIDIA, are you using internal embedding models, or you are using the open source, and same with VectorDB and the graph?
Yeah. So Jacob had shown actually a chart in his opening talk. NVEmbed is one of the embedding models that's the leader on the leaderboard for embedding models. That's the embedding model that we're using internally. So we have NVIDIA NeMo brand, which stands for Neural Model, NeMo Retriever, which are available as inference microservices that are optimized for inference already. So we use those. So it's Milvus database that is inference optimized, along with the embedding model. And then there is the NV re-rank, the re-ranker model, which was also in that leaderboard. So these are the models that we use. All of them are available as inference optimized models. And some of them are actually publicly available on Hugging Face. You can check them out as well. So we use wherever NVIDIA technology is available, like the retriever, re-ranking, embedding, and the LLM models themselves, they're all inference optimized, available on NVIDIA's ai.nvidia.com for customers to try and use, and for us also for internal use. Those are the ones we use.
Thank you. Unfortunately, we're a bit over time, so the rest of the questions will have to be taken offline. So thank you once again. Please, round of applause. Right. So our next speaker is none other than Raza Habib, who actually is the second year with us. Last year, who was at the Transformers at Work in Amsterdam, and now he joins us once again in San Francisco, his hometown for now. So Raza is the CEO of HumanLoop, a workspace for developing and evaluating LLM applications. He was also a founding engineer at Monolith AI, where he applied AI in mechanical engineering. And he has also worked on many speech systems at Google and also holds a PhD in machine learning from UCL. So in his talk, he will address questions on building reliable agents, how to evaluate AI systems, and what are the skills that AI product teams need to build LLM systems. So please welcome Raza Habib.
All right, hello. Nice to meet everyone. I'm Raza Habib. I'm the CEO and co-founder of HumanLoop. Thanks very much for the introduction. I'm just going to wait for a moment to get my slides, and then I will start. This is my fault. I sent them in late. How are we doing, Jakob? All right, here we go. Okay, fantastic. Thanks very much. So I am going to be talking to you guys about best practices for building with large language models and trying to build production applications with LLMs. And just before I start, how did that happen? Okay, just before I start, I thought I'd just open with a little bit of background on who I am and what HumanLoop does, just so you have some, why should you listen to us? Like, why do I have a right to have a perspective on the answer to this question at all? Okay, now, there we go. So a little bit first about HumanLoop. So what we do is we help companies who are trying to build applications with large language models to both evaluate those systems during development and in production. So really relevant to what you were saying about the different touch points during a RAG system, providing that instrumentation and the ability to have that continuous improvement loop really quickly. And then we also provide tooling for non-technical domain experts to be deeply involved in that process of doing evaluation and doing prompt engineering. And so we've been doing this for about 4 years now. We've done it at scale with a whole bunch of companies that you likely would have heard of and many others as well. And then in addition to my work at HumanLoop, I also run this podcast called the High Agency Podcast. And once a week, I chat to a sort of product leader, engineering leader who has over the last year actually deployed some form of AI product. And so the sort of what I'm going to do in the talk today really is just share some of those experiences. So it's not going to be an academic talk. It's really going to be lessons from both those people who I've spoken to and also my own experiences in helping these companies get things into production. I'll try and focus on what sort of repeatable lessons we've seen have worked, but also give you a flavor of what are the different things that people are building. It's not all chatbots and customer support systems. So I actually gave a talk with the same title, more or less, at this conference last year. And so I thought I'd just start off by reflecting a little bit on what's changed since then. So the first thing I would say that's changed since then is many more companies are now actually building with LLMs in production. So when I gave this talk last year, one of the first things I did was try to persuade the audience, and at the time it was a slightly more academic audience, that you could actually do useful things with LLMs. And people were skeptical at the time. And I came up with this long list. But what's interesting about this list is every company on this list more or less was a startup. I couldn't actually think of an example at the time of large enterprises who had deployed LLMs into production. That was only a year ago. And now, we've already seen so many examples today. It's become way more normal for big companies to have done this. There's a lot more infrastructure, a lot's happened to help that. The model capabilities have obviously continued improving. And now we all watch these leaderboards anxiously and see new ones coming out every day, every week, etc. It's mostly been fairly incremental progress, like smooth progress, maybe till this week with O1. But there's definitely been improvements. And the other thing that's changed is open source has gotten a lot better. So the top spots on the leaderboard are still dominated by, I'm not very good at using this clicker, am I? The top spots are still dominated by the private models. OpenAI holds the top 4 slots, but Llama and Mistral and others are now near the top, and it's possible to have private deployments of these models. And the other thing that's changed is that knowledge has just become way more distributed. So when I gave this talk last year and I spoke about RAG, this was new information to the majority of the people in the audience. Like the idea that you could use this to mitigate hallucinations was sort of surprising to people. Now it's distributed, like no one is asking these questions anymore. So that's, I think, some of what's changed. I think the fundamental challenges haven't really changed. So what makes building with LLMs difficult, I think, is still the same, which is one, evaluation continues to be really hard. So we all know that compared to traditional software, we're dealing with stochastic systems, but that was always true in machine learning anyway. Part of what makes evaluating LLM applications so difficult is the generality and the subjectivity. So it's hard sometimes to even say what the correct answer is. The other thing is that prompting has become the dominant way of adapting these systems. So whereas a few years ago you would collect a data set, you'd fine-tune a model, we write these natural language instructions and compress what was weeks of work into minutes of prompt writing. But the flip side of that is we have this extra artifact that's floating around that is kind of like code, kind of like a data set. It affects how our models perform. And so it needs to be versioned and tracked and controlled in the same way as code. Changes to prompts have impacts on an application. It's not super straightforward to reason about exactly how when I change a prompt, it's going to affect my application. And so that's kind of an ongoing challenge. Hallucination. So models saying factually inaccurate things or answering questions where they don't have knowledge baked in continues to be a challenge. And then latency, privacy, cost are the practical considerations that sort of stock bind all of these things. So people are concerned about data going to third-party systems. The models are very large and therefore more expensive and slower. And although there's been improvements in all of these areas, they still remain challenges. And then defensibility is something that I think people think about a lot. The barriers to entry to building these systems have gone down massively. And so when you are investing lots of resources into building a system, people then reasonably question, what's to stop others doing similar things? So, damn it, I keep getting new slides. Is someone else doing this for me? Okay, thank you. I'll tick them along if that's okay. One other thing that hasn't changed is the structure of these applications is largely the same, right? So the way I think of most LLM applications is they're composed fundamentally of these LLM blocks. There's pre-processing and post-processing code. There might be other stages to it, but the core pieces of the LLM part is always the same thing. There's some kind of base model. Maybe it's fine-tuned. There's a prompt template, some kind of natural language string that you're going to feed context into. A strategy for selecting what data goes into that context. So it could be via retrieval, it could be coming from a function call or from a user. And then this is often augmented with tools or function calling such that the model has the ability to call out to other systems. And then you might embed this in a loop, you might connect it to other systems, but this is the kind of core atomic unit that we're kind of playing with. And I think my favorite example of this is one of the most successful earliest LM applications was GitHub Copilot. I always use this example because I think it was the first sort of real highly retentive in production at scale application. And again, they have a small 12 billion parameter base fine-tuned model. There's a structured prompt template that takes the code immediately behind the cursor of the person who's typing, puts that into the context of the model. And then finally, they sort of use, I said tools as function calling, but that's left over from the last slide, sorry. They use a feedback strategy for end user feedback. So they look at How often are the suggestions accepted? How long does that code stay if it's accepted? And what's the edit distance between what's accepted in terms of what stays and not? And they use that to drive a continuous feedback loop. So I think this has like, this is a one block LLM application, but it has all of the components that we might think of and is like a good real world example. When I came to write this talk a year ago, this was one of the only big enterprise applications that I could talk about at the time. But one of the things that's changed since then is there are a lot more examples now. So I thought what I would do briefly is just talk through each of these 4 companies that I know reasonably well and what they're building with. And they all do something slightly different with LLMs. I think it's interesting to hear a few examples of real world use cases, and then I'll distill the lessons from these in the sort of 10 minutes that I have left. So Ironclad, one of the larger startups, quote unquote, near sort of pre-IPO company in the Bay, helping lawyers with contract management, lifecycle processing. And they've built into Ironclad quite a lot of agentic AI features. And so one of the things they can do is lawyers can create a playbook in Ironclad of how a standard contract should be negotiated. So maybe every time we have a particular NDA, we should never accept durations beyond this length, or those kinds of things. They build out that playbook, and then the AI system, when new contracts comes in, reads them and autonomously rewrites and negotiates the contract. And for their largest customers, something like 50% of their contracts are now automatically negotiated. Sorry, can I have my slide back, please? Thank you. And so in building this, there's like a few lessons that Ironclad had to come up with that I think are particularly interesting. So firstly, they skipped RAG. They went straight to agentic systems. And when they first tried to do that, they found it very hard to make it work. And in order to actually get this to work, they built an internal tool called Rivet, which I would recommend people go check out. But it's a visual programming system for prompting that shows you how the data flows through the system and allows them to debug in real time every stage of this. And they say that that was like absolutely critical to making this work. The other lessons that I think the Ironclad team recommends that people take is, and this is why they went for agents straight away, is that a lot of companies are doing incremental things with LLMs. They're sort of adding a chatbot, they're trying to make customer support a little bit better, and it doesn't move the needle for their customers that much. And what they really did well, and I'm going to talk about Gusto in a moment as well, and they did the same thing, is they tried to see like where in our application actually are people getting bottlenecked the most, where are they spending the most time, where an LLM could actually help. And so in both of these cases, and I'll talk about Gusto in a moment, they're saving their customers many hours from a workflow that previously they were doing manually, rather than something that looks smart but doesn't actually move the needle that much for their customers. And so so the CTO's advice from Ironclad is that you should take fairly big risks and bet large on this, because the space is moving so quickly that if you don't, you'll likely be disrupted. Gusto has done a couple of things with LLMs. One that is, I think, more conventional, which is they've built an internal customer support bot. In their case, it's slightly subtle though, because they have a very large number of small customers. They serve very small businesses, and they do something extremely complicated, right? They're advising people on payroll and tax and accounting. And so the long tail of possible customer support queries for someone like Gusto is enormous. So it's not just like, how do I cancel my account? But it's, I live in New Jersey, I cross the state into New York, what happens to my payroll, and these kinds of cases. So complicated expert questions. And they have an assistant now that is sort of indispensable to their support workers. So if they've sort of done the test of people having it or not having it, and it moves the needle enormously. They started off distributing the ability to build AI features across the whole company, and that resulted in mostly incremental improvements. And so one of the big lessons from them was actually, again, centralizing in order to try and figure out which are the places where if we build a feature is going to move the needle the most for our customers. And the thing that they've ended up automating is their report builder. So there's something that accountants go into the app, they would build a report on top of data. It was 3 or 4 hours of work per report previously. It's now 1 or 2 minutes with an AI agent. And I'm going to skip going into detail on Vanta and Hex because I can see the times that people are going to ask me about it in questions afterwards. But just briefly, what Hex has built is an AI coding assistant for data scientists. And what Vanta has built is the ability for you to automatically review InfoSec policies. So when you take on a new vendor, you can check whether or not they're compliant. And those are 4 quite different use cases. They're all a little bit different from the standard sort of customer support use case, but building on the same technology. And I can sort of share lessons in each of them. Okay, so what do the teams who do this get right? Like, what have we seen being the consistent patterns of success? So there's this quote from Colonel Boyd that I really like. He used to say, people, ideas, machines, in that order. And that's also been what we've seen with the teams that tend to succeed versus the ones that don't. So the first thing that people tend to get right is team composition. So before, it was the case that machine learning was something mostly done by machine learning engineers. You were training your own models, you were fine-tuning them, you were building data sets. It was a particular skill set that's not really the skill set that's at the core of building with LLM applications. Mostly people are now calling APIs. And on the other side of things, you have people who are pure product engineers or software engineers, but maybe don't have any machine learning experience. And what we've seen is that these projects tend to succeed best, one, when they're led by, or the sort of ratio of people on the team tends to be mostly traditional software engineers with more product focus than machine learning focus. Because fundamentally, you're not trying to optimize a model, you're actually trying to optimize a product. But with at least some input from machine learning people, because you still have to do things like build a test set, iterate against metrics, understand how to do evaluation rigorously. And so if you miss that skill set, you tend not to do well. If you have too much of the machine learning side and not enough of the product side, companies tend not to do well. And then the other thing that we've seen is that domain expertise ends up being, as it always is, extremely important. So the teams that do best give the domain experts the ability to actually drive the process themselves. So the domain experts are writing prompts, they're involved in doing the evaluation, they're reviewing data, they're looking at logs, and they're core parts of the team. The second thing that we see a lot is teams will start off, they'll get a version working, but it won't have high retention. It won't be something that is good enough to go into production, and they'll plateau for a while. And usually this is because they don't have good evaluation. And I'll talk about why evaluation is hard and how we can fix it. But you're making a combinatorially large number of decisions. You're trying to decide over prompts, models, multiple times if you've got an agent, retrieval systems, chunking strategies, re-ranking, and each of these things is independently affecting the outcome. And so if you kind of are just looking at a handful of examples, or if you have only one metric that's not allowing you to see how each of the different components are working, then actually it's very hard to systematically improve your system. And so people sort of reach a certain stage and then they plateau unless they have really good evaluation. And the last point is sort of related to the second one, right? And obviously I would say this because Human Loop helps you build this kind of tooling, but I do think it's the last point, right? So it really can help if you have these first two things in place, but you've got to have the right processes and the right people in place first. And then the tooling can make it easier, but it's not going to solve your problems without that. So there we go. Okay, so I think the most important of the three, though, by far, is having good evaluation. And I think evaluation matters at every stage of development. So the first place where people start when they're prototyping, they're trying to find the right prompts. Usually you want to have very fast feedback. You want to be in a REPL-like environment where you're getting interactivity, you're able to run something and see some kind of improvement quickly. And usually at that stage, people are looking at just a handful of examples. They're trying to work out, is this thing even possible? Once you progress from that, the next stage is starting to build evaluation criteria. And here, I think this is where people should really start looking at their data, doing test case analysis, finding the places where the model's currently failing, and then trying to write an evaluation, so either a code-based evaluation or even just an annotation guideline for each common failure case, and building a test set against those before iterating further on every component of their system. And then you have that test based in development, you iterate against it, and then post-production, you still need to be able to evaluate the system to see how well it's working. And those are places where two things end up being like super valuable. One is end user feedback, and this shows up in the form of votes, thumbs up, thumbs down, but it also shows up in the form of the actions the users take, whether or not they progress to the next stage, any corrections they might make of generated text. And so you want to be logging all of those things and having them feed back into your continuous improvement system. And you also want these things integrated with CI/CD. So another problem that we commonly see is people end up playing a sort of whack-a-mole type game, where if they don't have good evaluation coverage and they don't have these things integrated in CI/CD, they'll make a change that fixes one problem, they'll change a prompt, or they'll update something in their retrieval system, and then they'll find they've created problems elsewhere and they don't know about it till later. So you want good coverage on all of these things. So if I was to kind of just describe the recipe for doing this in detail, we'll come back to that slide. I should have said that earlier. Oh, no, these are going backwards. Okay. I'm getting my slides out of order. I don't know why. Can you give me the next slide, please? Yeah, so if we sort of try and think about the process in detail, then the kind of mental model I have for this is you want to be running this kind of loop, and I've borrowed this slide from Hamel Hussein, as quickly as possible. And so the tooling we're building at Human Loop is trying to give you the tools you need to do this very, very quickly. And so the idea is that you start off, as I said, with sort of a rough idea of what you want. You've built the first version of the system. You've written usually code-based assertions early on that cover the common test cases, and then you start building a detailed evaluation set. And it's very hard to just sit down and write all the evals up front. Typically what we see is that the evaluation criteria that you have co-evolve alongside working on the prompts and working on the other parts of the system. So you'll discover new failure modes as you're iterating, and then you'll create a new test for those failure modes, add that to the test set, and keep going till you feel like you have good coverage across all of the common ways in which the model can go wrong. And so typically at that stage, people are using code-based evaluation and normal metrics. So the normal machine learning ones, as well as code assertions. So accuracy, F1, precision, recall for things like the retrievers. But also people are increasingly using model as judge. And so you'll be using a prompted LLM that can evaluate some of these criteria. And usually it's not as accurate as a fine-tuned model, but it's often on par with human judgment, and it's much cheaper and much faster. So typically what we see people do is they will start off with a sort of LLM-based criteria, a kind of annotation guideline to the model. They'll get humans to review some of the outputs from that, and they'll iterate on that for a few cycles until the correlation between the model and their human rankers is high, and then they'll start relying on the model as their annotation tool rather than having humans do the annotation. Once you've got that set up, you can then iterate very quickly, and there's really two improvement directions you can go in. You can either modify the prompts, or you can fine-tune the models, excluding the retrievers and other parts, which obviously have their own components. And so if we were to just kind of summarize that whole process, the first thing I would say is like the most important step throughout this whole thing is to be able to look at your data. So people need to be looking at individual test cases. They need to be looking at data points, looking at what the model output is. And good tooling can make this easier, but just you can't not do this step. So this is, I think, the most important part of the whole evaluation process. I put it as number one, and you could probably do it at every stage of this. And that's where you do the error analysis. You'll do manual labeling. You'll start building up your evaluations. You'll build code-based evaluations, and you'll probably build more scalable LLM as judge-based evaluations. The other thing that the best teams do well is they instrument everything. So at every stage of the pipeline, they're able to see the inputs and outputs. So from the retriever, from the re-ranker, from the prompt, at every stage they have that, and they also have that augmented with the ability to do evaluations and to iterate on those things quickly. And the final point is post-deployment, then end user feedback is really, really valuable because these are such subjective applications. And so, you know, ideally you would start with the end user feedback, but you have to obviously get to a certain level before you can deploy. And then post-production, you want to be continuously improving things. So you don't want to deploy and just stop. You want to use that feedback to find where the new failure cases are, to augment your evaluation set, to then continue running this feedback loop. And usually the people involved are both the non-technical people and the engineers. So what we see is that the companies that do best are involving non-technical people in prompt engineering and in reviewing the evaluations. So at Duolingo, for example, the linguists write the prompts. At Vanta, they have technical security experts who are both looking at evaluation data and also helping update prompts. And I can give many more examples. And the other thing that I think is quite different from a lot of traditional machine learning development is typically you want a family of independent evaluators, each of which is measuring kind of one failure mode or one attribute that you care about, whether it's helpfulness, speed, cost, etc., rather than having kind of one number that you push up. So when you're training a model, often it would just be the loss on the model. Whereas here, you're actually looking at kind of a holistic family of evaluation criteria that give you a scorecard on how well the model's performing. And the last thing I will say is that, you know, the right tooling really can help here. So, you know, what Human Loop is trying to do is give you tooling that allows you to do that logging, that gives you the space for the non-technical people to iterate, allows you to create evaluators, log the data, monitor, and run this feedback cycle very quickly. But the tooling will not help unless you have the right people and the right mindset in place. And so one of the other things that we've seen the best companies do is they educate their software engineers who are not from a machine learning background on the importance of evaluation and fast iteration. Because if you come from traditional software and you're used to mostly operating with the deterministic systems, or you write unit tests and you write integration tests, then this idea of kind of like ready, aim, fire where you will build something and then keep improving it against a test set, is a little bit more alien culturally. But if you can get that sort of culture change right, then I think tooling like Human Loop can make a really big difference to how quickly you can run this loop. But if I was to summarize, I would say that there's kind of three things that the teams that succeed tend to do well. One is they get the right teams together, so sort of 4-to-1, 5-to-1 ratio of kind of like normal engineers to ML people, very deep collaboration with domain experts. They make evaluation the core of what they're doing. They launch quickly and they iterate very fast. And they also, even before that, one step earlier, they think very carefully about which problems are worth solving. So they're making sure that if they were to succeed, the LM problems that they're solving will be ones that will have a large delta for their customers. And then finally, they put good instrumentation in place. And whether they do that with something like Human Loop or they do it with something else, but they're making sure that at every stage of their system, they are evaluating things and they are able to look at the logs and improve them. So that's what I wanted to say. Thank you very much.
Thank you, Raza. Thank you so much. It was a really great talk. I enjoyed it. So we have time for probably 1 or 2 questions from the room. Yep.
My question is on the order of magnitude. What would be the appropriate number of samples for a test set?
It's a good question. So what we see in practice is that people have test sets that are on the order of like a few thousand data points. So not necessarily millions of data points here. And they're trying to have good coverage. So we also see two things. We see people build like a core test set where they've kind of got cases that are supposed to be representative of what's in production. But then they also have failure modes that they find, like edge cases that they know are very important, but that the models commonly fail on. And they'll often build a separate like edge case set. And the reason being is that when they have changes to the model, they want to make sure they don't regress on those edge cases that are common failure modes. So often we see at least 2 different types of set, if not more, but sort of one edge case set, one production representative set. And of the order of a few thousand points is often enough to get like reasonable scores.
Thank you. Let's do one more.
For the user feedback and evaluation, right? Because we are probably going to be launching in like beta or alpha, right? How do you recommend users stay engaged with your application? Because if too many wrong responses are delivered by your app, users are probably going to, churn, even your internal users, right? Because everyone's day is packed and they're looking for a quick response and not really trying to babysit an LLM app. So are there any recommendations on that aspect of it?
Yeah, so I think one of my favorite examples from a real company in terms of how they thought about this was a company called Pseudowrite. So Pseudowrite is a company that is writing a writing assistant for novelists. And so they have a writing editor and lots of AI assistant features that help them to write better. And each assistant feature has its own instrumentation and testing. And what they do is they first release to a small group of users to kind of get feedback. And then once they've done that, they release to a larger one. And then they measure a bunch of different metrics post-production. So they're measuring, so the way it works in their system is there's a kind of editor on the left-hand side, like Google Docs, and the AI suggestions appear on the right. So they measure, like, did the user accept the suggestion? Did they edit the suggestion? Did they regenerate? How many times did they regenerate? And then did the text stay in? And they do that for each of their features. And they're using that to guide like whether or not, so that signal allows them to guide, and they iterate on the prompts as that number goes up. But the other thing that I think is interesting about them is they're very ruthless about what features they keep. So they actually launch a lot of features like this very quickly. They measure those attributes fast. And if they don't get good signals relatively quickly, then they cut that feature and they do something else. And they have a very high retention product now. I think there's 14,000 novelists, which is like, a pretty tricky market to break into, who are using it daily. And I think the reason for the high retention is exactly this, the speed of experimentation that they have.
Awesome. Thanks again. Please, a round of applause.
Thanks very much.
All right, let's get the slides ready for the next speaker, who is Julia Kiseleva. She is currently building safe and reliable AI agents at Multion after nearly 6 years of experience in Microsoft research. And of course, she has a lot of experience in evaluating agents, and especially with having humans in the loop. She also has been a contributor to research initiatives like the iGlue contest and the Agent Eval tool. But today she will be discussing challenges in how we develop these agents that usually have to deal with natural language as inputs, how suitable datasets are not pretty much existent today, and what evaluation platforms we need to build to do this effectively. So a round of applause for Julia.
Thank you so much for introduction. And today I'm especially excited to be here and present this work. First of all, because the previous speaker made it very easy for me to don't need to convince you anymore that how important is evaluation. And another exciting part that actually this paper just got accepted today in the morning at AMNLP. So it's big kudos to all of my collaborators on this. So, and prior to even start, so how did we come up with this idea? So I have been in Microsoft research last September, where we released AutoGen, which is now one of the most used frameworks for building agents. And I have been just blown away by how people take it and bring it to all kinds of applications without a lot of attention to how you can evaluate those type of agents. And me coming from the web search, where for about like 10 to 15 years, the whole community have been focused on one particular application, like as usually it was like 10 blue links, and it gets a bit more complicated, and how we actually push it forward with proper, at the time, evaluations for the rankers, which used to be, which is still as NDCG, which is highly correlated with human annotations. And I was just kind of a bit scared as well. So people use it for all kind of applications without even knowing what kind of needs the end user have. And we all focus on, like, when we talk about evaluations and in machine learning, focus on success. But how about we focus about utility? Because now we're building all these agents to the end users, and we want to increase utility for them. So it's no longer only about user engagement, no longer about how much time you spend. We actually want to develop the applications where you have users engage with that. So we need to have a scalable evaluation metrics. And currently, Agent Eval is also part of the AutoGen, so you can go to the library and just use it for your applications. So, so what AutoGen is about is this agents communicating to each other and solving tasks for you. So, and we have seen that developers, and not all of them have been trained for with all these ideas about machine learning. Like, we wanted to develop the easy, accessible metrics for them so that they can assess the quality of the approaches they're using. So that was our motivation. And we wanted to scale to kind of leverage LLM as a judge. Because again, we're building tons of new applications. It's no longer like just a web search how it was, and very static view of that. And that was great. And that was, I think, one of the success of the web search in our early days, because we knew how to evaluate it. We knew how to do it with real users through the A/B testing, and we can scale it up. And also, one of my personal goal was for that to kind of empower the developers of these agentic systems with the right tool and make them aware what the users thinks about the application. So, and just here again, we in machine learning always focusing on success. So especially like in all of the parts of machine learning, including the robotics, where you have a trajectory and you want to lead, you kind of want to have a success metric to it. And let's focus on a task where we do have a success metric defined for this work, just because I wanted to have some kind of grounds before going and publish this paper, so at least something of that is believable. So, but at the moment, we're facing the challenges such as your metrics can be obsolete. So when ChatGPT is generating the email for you, and if there's no two emails generated and you can compare them pairwise, you're just excited that something is done for you. You're gonna tweak it a little bit and then send it, right? So is it success or is it not a success? So it's maybe also time for us to figure it out, like how we define those successes. So there's two trajectories leading to the successful output. Which of those trajectories is better? So, and those questions came from my previous research where we were designing the agents in Minecraft following the instructions natural language, which is now sounds really trivial, but we started before the LLM outbreak. Was not that easy. And through a lot of evaluations, we figured it out it's no longer about success when you have put it in front of humans, because humans have these judgments, like this agent is too fast, this agent is too slow. And that got me to the idea that actually the criterias are important. And the previous speakers pointed it out as well. So it's actually utility, and it's maybe multi-dimensional utility. So it's not only one success metric. I'm not telling you to avoid the success metrics. Like, for example, if you have a car, just automobile, so it's going to be acceleration no matter what. Like, has been like that 100 years ago. It's probably going to be the same metric of success of the car in 100 years. But the weight of the battery is a new criteria, which happen to be now have an important contribution to the whole success, but it's new. And as previous speaker pointed out, you would need to reassess your criteria along developing your system, because your system and the way how a system behave introduced a new way of how users finds the utility. So, and as previous speaker pointed out as well, so like it's nice to have these criteria, but we were thinking like, how can everyone think about those criteria up front? So, and we decided to use LLM for that. So LLM can come up with you with a criteria. So for that, we have a critic agent, to which agent we explain, like, and as for developers, as a developer of those systems, you need to explain, what do you want to achieve with this, what's description of your task, and you provide a couple of solutions. We suggested to provide a successful solution, failed solution. That's just one of the way to do it. So, and then, so the critic will come up to you with a actually number set of criteria. And this is, for example, for one of the most frequent or like most of the used data set on the math problems. In the paper or like in the blog post, you could see how we actually ran it for other data sets. But since we are all kind of a little bit experts in math, you can kind of see with your own eyes how well or how badly it's performing. So, and this is like one of the snapshots of criteria the LM came up without us, any intervention from us, including the description and including the accepted values. And here I want to emphasize that you need to keep the accepted values the way LLM is showing it to you, if you want to use LLM as a judge. So, and then you take your output of your solution, which is just logs of produced by the agents, and apply the quantifier agent, which will quantify each of the solutions according to the criteria you specified. By the way, the AutoGen easily can allow you to change the criteria. If you think that LLM missed some of the criteria, please point it out there. So like it will be happily given it to you. And probably you will have a question to me, because we're all very excited about LLMs, but sometimes a bit suspicious. Like I hear it all the time. So, and then like, how can we trust the quantifier agent? And so you don't have to trust anything. So you can just run that as an experiment. I always tell to my team currently, like if you have an opinion, you better wrap it up as an experiment and have some number to prove if you're wrong or right. So, and here is the same. So we have a verifier agent, which can highlight to you to which of the results, not necessarily you don't have to trust, but they are not as stable as you would like it to be. For that, for example, we have done like error analysis of those criteria. It's a result of the quantifier. And here you see the success is darker colors, and successful and unsuccessful results are a bit lighter colors. That's where I wanted to check myself if we are doing something correct, because you expect that failed results will be low on some criteria than others. So, and here, for example, it gives you more idea. So like here, we have three methods we run it for. So blue is autogen, green is GPT-4, and the combination of orange and yellow colors is React. So, and here you could see that how like various of this, by the way, autogen was always outperforming in terms of accuracy for solving the math problems, but it's not outperforming all the other solutions based on different criteria. And you, as a designer of the agentic systems, need to decide which criteria is important to you. And here I want to give you some anecdotal examples, since I spend a lot of time thinking about that. First time I ran these experiments, for example, on the math problems, I found that one of the criteria was code efficiency. And then it crossed my mind that autogen actually writes code to solve the mathematical problems. And that's what gives us high accuracy. But imagine if you're designing the tutor for the students for the math problems. I have brought this example previously, and some people tell me like it's a way to go anyway, so it's up to you. That's where I'm saying to you that like you need to figure it out as an agentic system developer, what kind of criteria you want to emphasize in your solution. And at least we give you a tool to be aware what you're doing and on what what you can expect. So here you can see the error analysis where you have a slope of the performance. So where like actually failed cases getting harder. And in this case, that's where we think that's one of the ways to kind of see if the quantifier doing a good job or not. And it's not always consistent. And that's when you probably don't want to, at least I would not recommend to include it into your like evaluation of your system. So, and another thing I wanted to point out here is that I have seen a lot of those results. And then, for example, if we look back at the like accepted values, like not clear, moderately clear, very clear, and so on and so forth. We have seen some experiments with humans, and the exact label matching might not be how human gonna label it. But most of the time, the relative numbers are gonna be the same. If the LLM is telling you that A is better than B, that's probably gonna be the same if you ask the humans. Would be the same, would you have the same labels? I'm not sure. And by the way, I'm not sure that you need it, because in the end of the day, we just wanna move it up. We don't need to kind of match that exact labels. So, and here is another example of, I think previously mentioned, is just for you to understand. So what we did here, so we were thinking, okay, can you just get those criteria without giving the critic as inputs the failed and successful examples of your systems? So just describing the task. And you can, and here is a red, it's a kind of red line, but solution brings the criteria as well. That's when like actually you changing the solution while you go. Similar to like, do you want to include the kind of the coding efficiency into your math problems or not? So that's going to be totally up to you. We're just giving you the instrument to understand what you're doing. So, and here is another example of like how we were thinking about like what's the distribution of the quantifier agents and like when you should not trust it. So in our experiments, like how can you basically verify if you can trust the quantifier? Because with a critic, you can easily, as a human, look over those criteria and figure out, I want this criteria, I don't want this criteria. But with a quantifier, if you run it at scale and actually want to rely it as a metrics, you want to have some kind of grounds to make sure that you're doing the right job. So here, for example, again, error analysis, you could see based on the average success score, they're almost the same for failed and success cases. And that's where we think that quantifier couldn't do a job within distinguishing the different cases. And that's okay, that's a room for improvement, but at least you need to run it at least once to see that the kind of score, the distribution of your scores are different. And another thing you would, it actually was quite a hard experiment to come up with, is that you can tell me about those numbers, like, Julia, how can you be sure that, like, if the quantifier returns you a higher score compared to other example, how can I trust it? And we asked ourselves the same question, like, how can we trust it? And what we did, we tried to do the adversarial experiments here. So we basically take the solution, let's say from AutoGen, and we corrupted this solution on purpose. Just remove part of the results, for example. And then what we expect from quantifier is to understand that this solution is worse than the one which is complete. That's one step further towards ideas where most of those developers online who are not on like also like companies online do not have a good idea what is a success, what is not success. Some point we need to deal with ideas that it's actually like we need to come up with new paradigm, and that's maybe one of the steps towards build a trust towards the LLM giving you scores for the solutions. So and again, like the error analysis is one of those kind of nasty criteria we found out for math problems. Was not the only one. I'm just here like trying to summarize it for just give you the overall message. Was not behaving as expected. So that's why I would not use it. At least like you can have this criteria maybe is okay, but the quantifier cannot do a job to assess if this is a good one or not. So, and I wanted to give you the is my conclusions here. So, and after finishing this work, I moved to Multion. I joined about 4 months ago, where we actually dedicated to build the agentic systems, basically the personal agents, which will help you with a daily task. And we dedicated to make sure that it actually brings the utility to the end users, and for that, we need to make sure that our evaluations are scalable and they also reliable, and they actually delivering to the end users the best possible solutions. And we want to iterate on this. So, and I think this work has a lot of potentials. I'm super happy that like NLP community was so kind of open-minded, because it's a bit of a unusual work and is like not following the traditional strategies of evaluation. But I think we now need to move fast with how we assess the quality of those systems, because the potentials are huge, and we just need to make sure that we are delivering something, especially if you work with end users, so that you're delivering something which is reliable, safe, and also like it actually brings utility to the end user. Thank you. Yeah, and it's this AutoGen, so it's part of the AutoGen. If you want to play with the agent well, you can go right away and just look over this and look over your data and see how useful it is for you, and give me any feedback in any form possible. We would love to learn, because we have tons of experiments on other data sets as well.
Thank you. Thank you so much. We have plenty of time now for questions. So anyone in the room or online, for the people online, I would suggest you type them during the talk so I can get to you first. But yeah, let's start with the room if anyone has a question. Maybe Nick, I can start with one more from a builder perspective. You mentioned all these kind of multi-agent systems collaborating. How do you see the orchestration and the communication between the agent happening? Is it clearly defined, or is it a tricky part to get right still?
You mean the orchestration when you have multiple agents talking to each other?
Right, yeah.
So
how do they exchange data? How do they inform each other of what to do and so on?
That's tricky. So we definitely need to go through a lot of experimentations. There's a number of works now where people think about this. So one of the most promising works I have seen is actually, it's a trace work actually coming from Microsoft Research as well. So, and that's where like the orchestrations is defined as a graph. And you need to define which agents see each other, which agent doesn't see each other. So I believe that that's going to be one of, like when we have a better way of understanding what types of orchestrations are good for your applications, that would be breaking through. And I think that's like having a proper evaluation in place is one of the ways to go, because now if you have like a number of hypotheses you want to try with different types of orchestration, you also have a very kind of a framework for seeing like which one works better for your application. I also see, I'm like at the moment, I'm not sure we are ready for the general type of orchestrator, but definitely we should start like kind of dealing from the application types of kind of starting scenario based and then maybe going to the more general orchestrator.
So what you're hinting at is that we're not ready yet for one solution. You have to tweak a lot on your kind of problem.
You need to be ready, but like you need to be careful towards like running those experiments reliably and kind of having things designed for you, because like also it's multi-on, like one of the challenges we are facing, not challenges, also like in a good way, is that we're trying to develop the next type of agents which can make actions on your behalf. So we need to be very reliable in terms of making actions on your behalf. For example, making a payment on your behalf. So, and that's why we need to kind of test many different hypotheses one by one before going to the general orchestrator.
Great, thank you. Any more questions?
Hi, I don't have a question, but I wanted to kind of piggyback on the question that you had to present some perspectives. There are, in the past, in the agent world, there have been many models that have been tried, like blackboard architectures, like auctions, and planning, of course. So depending on the domain and what actually makes sense for the use case, I very much think that in the future there will be a lot of different of these frameworks that will be built into platforms, and depending on the use case, people will use it. Because if you put some of these things out in the public domain, not so much for enterprise use cases, maybe some of these things will make more sense, like the auctions one. You want to go with the one who has more better ratings or reviews, and the one who bids better, in terms of cost maybe, or there are a slew of these kinds of architectural patterns that have been talked about in literature and actually experimented with in the previous iteration in computer science back in early 90s, 2000s. So all those things are good candidates as well, but it has to be practical and applicable to the use case.
Yeah, thank you so much. That's exactly right. And I wanted to bring up one of the examples, anecdotal examples we have encountered back working in Microsoft Research. So like planning is a very important part. Like, how do you need to do planning? Should you do it outside of agentic loop or inside the agentic loop? For example, we have seen a lot of things where people start writing tools to help agents to accomplish the tasks. For example, there's this Gaia dataset, which was published in November, I think. So it's like a 3 level of difficulties. And one of the tasks is like, you need to watch the YouTube video to answer the question. Great. So people start writing the tools for agent to have to kind of write, to watch these videos and answer a question. Is it intelligence? Questionable. But did the experiment where we didn't give any tools to the agents and kind of let them plan themselves. And they figured out that they need to install the library to transcribe this video, and they know how to deal with the text. Is it more like sounds like intelligence? Maybe. So this is all good questions to ask, but I'm totally agreeing that now we will have a lot of experimentation running for different types of ways of how we do the orchestration, where we do planning, how we do planning, and things like that. And I hope I kind of did my part to make sure that you know about the framework for the evaluation, because you need to be always running, to answer those questions, you need to run a lot of experiments and have a valid way of evaluating your different types of agentic frameworks.
All right, thank you so much, Julia, once again.
Thank you.
Right, so this was the first section of our workshop. So we'll take a small break for 15 minutes. We'll be back at 2:45. We have coffee and bites for everyone in the room, also a demo of our platform. And yeah, we'll be back. For those online, if you want to stay engaged, we'll play a little quiz with some AI questions. And yeah, see you soon. All right, everyone, please let's start taking our seats so we can continue. I see a lot of interesting conversations, but keep some for the after party. All right. Hello? All right, welcome back, everyone. So we're having another short session of 3 talks. After that, we'll have another coffee break. And then for the final 2 talks and maybe a short panel with all of the speakers. So I'm excited to introduce our 4th speaker for the day, which is Michael Ryan. He's a research intern at Snowflake and currently a master's student in computer science and AI at Stanford. He likes to work on personalized NLP system in Stanford's Social and Language Technologies Lab, but he's actually also quite involved in DSPy, which is, and he's working on prompt optimization strategies. He will introduce language model programs and how he will demonstrate how this abstraction enables automatic optimizers to optimize the prompts and the weights of the program. And he will also introduce MiPro v2, which is the current best performing prompt optimization algorithm in DSPy. So please bring your hands together for Michael.
All right, hi everyone, I'm Michael. Thank you for the introduction. And so yeah, today I'm going to be talking about DSPy, which is the library for programming, not prompting language models. And what I know the title of the talk is Prompt Optimization for Language Model Programs, but what I hope to convince you by the end of the talk is that DSPy is a framework that will work no matter what the optimization paradigm is. So today it's prompt optimization and weight optimization. Tomorrow maybe something else comes out. And it's really the abstraction and the way of formatting your problem into this framework that really allows you to optimize many different ways. It's never been easier to build AI-powered applications. So you can see ChatGPT is obviously a very popular example. And if I ask, where is GitHub headquarters, it correctly tells me the address in San Francisco, California. But turning these monolithic language models into reliable AI systems remains challenging. So if I ask ChatGPT, when was Stanford University founded, it'll tell me actually the incorrect date. That's the date it opened, not the date it was founded. And it also tells you it was named after Leland Stanford, not Leland Stanford Jr., which is the correct answer. And this has real world impacts. So for example, Air Canada had a chatbot that was doing customer service, and it promised a customer a discount that didn't actually exist. And so the customer actually took Air Canada to court, and they had to honor that discount. So you really want your AI systems to be reliable. Every AI system is going to make mistakes, and the monolithic nature of language models makes them difficult to control, debug, and improve. So we already know how to build control systems and improve them modularly, and that's called programming. So we already do a lot of that. And that's where we introduced DSPy. So DSPy is the framework for programming, not prompting language models. And so with DSPy, you can use language models to build and optimize modular programs that are more accurate, transparent, and efficient than language models in isolation. So our idea here is not tweaking brittle prompts. So I'm going to show you this human engineered prompt that works pretty well for a multi-hop retrieval task. It breaks down the problem into search, lookup, finish steps, and asks the language model to walk through all of these. And this scores 33% on the HotPot QA benchmark with GPT 3.5. So it's a respectable score, and takes a lot of work to write a prompt like this. So what I'm going to do is show you all how we can write DSPy code that will automatically find us prompts that will beat this well-engineered human prompt. So instead, we can write a short Python program and let the program learn how to use the language model effectively. So one thing that DSPy gives us is composition via control flow. And so let's look, this is actually DSPy code right here. And I'm going to walk us all through it step by step. So DSPy is very inspired by PyTorch. So we have this forward method, and it will take in, this is a multi-hop retrieval question answering task. So we're going to take in a question and we want to produce the answer. And as I said, it's a multi-hop task. So we want to rewrite a search query and search, then rewrite the search query again and search, and then finally generate our final answer. So that's exactly what's happening here. We have a for loop for each hop. We rewrite the query in that self.generate query step. That's a call to a language model. Then we actually retrieve from whatever backend retrieval system we have implemented, and we'll get different passages. We'll use those passages to write another search query. And finally, with those 6 passages, we can generate an answer. And as I mentioned, there's 2 calls to a language model, well, 3 in total, 2 to rewrite the search query, and then 1 to generate the final answer. Then DSPy also gives us declarative layers, so we can specify exactly what we want input and output from our language model. So that's what we put into this init method here. This is where we declare that our generate query is going to take a context and a question and produce a query, and that our generate answer call is going to take in context and question and produce an answer. So given that, we can actually turn these declarative just inputs and outputs into prompts behind the scenes. And the last thing that we can do with DSPy is now optimize these language model programs. So I'm going to dig deeper into this particular call and show you all what a prompt behind the scenes will look like. And later in the talk, I'll be using this kind of cartoonish version of the code instead, because it's a little bit easier to look at. But just know that this is the same thing. This is the multi-hop retrieval. So given this statement that we want to take in a context question and produce a query, let's look at how DSPy turns this into a prompt template that can then be optimized. So really, we just compile these prompts into templates to start. So this is what a default prompt will look like in DSPy. So something like, given the field's context in question, respond with the field query, and we give it a little bit of a format to do this response in. But this is just a default template. We can further optimize on top of this, and I'll show you all how we do that in a moment. So DSPy can then further optimize this prompt jointly with all of the prompts in your program. Remember, our program had 3 distinct language model calls and 2 distinct prompts, and we'll optimize all of them for you. So we can take something like this, which maybe gets a score of 37%. We'll use the MiPro v2 optimizer, which is my research, and I'll talk about how that works. And then it'll produce something a little bit more like this. It's rewritten the instruction, it adds examples to the end, and if we run this on a validation set of several examples, maybe then we get 55 out of 100 right instead of 37 out of 100. So I'll show a closer example, and then I will show exactly how we make these. So here's what a prompt might look like after being optimized behind the scenes. So we'll have this plain text instruction, something like carefully read the provided context in question. Your task is to formulate a concise and relevant query. So that's been rewritten into more flowery language, potentially helpful to the language model. And then we'll also provide few-shot demonstrations. So here we have a full example of what the inputs and outputs should look like for the language model. So we'll give it some context. Remember, we declared that we wanted to take context, question, and produce a query. And so we'll take this context, which are these 2 documents that we've retrieved. We have this question about what year the first vampire-themed romance novel was published. And then we actually also include reasoning, because notice we said DSPy.chain of thought. And so that adds this additional reasoning step. And we're generating this few-shot example ourselves. And I'll talk about how we validate these few-shot examples too. But know that all of this doesn't have to be provided by the user. This is all generated. So it'll say, let's determine when that fantasy romance novel was first published, more details. And then we have an example search query. And so we'll put multiple of these examples in context. So this is just another example that we've generated. And this is what an optimized prompt will look like. So given that we wrote this short language model program in Python and let the program learn how to use the language model effectively itself, we can outperform this human baseline that I stated earlier. So if we use the same exact model, GPT 3.5, now we're scoring 55% on Hotpot QA. If we use a smaller model, Llama 2 13 billion, so at the time we were doing this work, that was state of the art. Things move quickly, but so you get 50% accuracy, which is above the human engineered prompt for GPT 3.5. And if you're willing to do some fine tuning, using our same library, just bootstrapping examples and fine tuning on those, you can even get 39% with T5, which is orders of magnitude smaller than GPT 3.5. And this is all possible thanks to new optimizers in the DSPy library, which tune the prompts and language model weights in arbitrary programs. So first they can bootstrap demonstrations, update the program with those demonstrations. So for example, if you want automatic few-shot prompting, we have dspy.bootstrap few-shot with random search. If you want to revise your instructions, you can use dspy.copro or dspy.mipro v2. And if you want to fine-tune your whole system end-to-end, you can use dspy.bootstrap fine-tune. And the cool thing about these is that they're composable. So if I want to first find few-shot demonstrations that work well, I can run dspy.bootstrap few-shot with random search, and then I can fine-tune on top of those, and then I can induce better instructions. So you can stack all of these optimizers on top of each other. And this works really well in practice. So I have 2 examples here. But there are dozens of examples in both production and research where DSPy is being used and excels in quality. So in May of 2024, University of Toronto researchers built and optimized DSPy programs to win the MEDI-QA competition by a nearly 20-point margin. So this task was trying to identify errors in medical documents, so specific sentences where things were incorrect. And they beat the competition, as I mentioned, by almost 20%. By optimizing their program in DSPy. And in June of 2024, University of Maryland researchers ran a direct case study where they were essentially, they had a human prompt engineer work on a prompt for 20 hours on detecting mental health disclosures on Reddit. And then they also wrote a program in DSPy to do the same. And it beat the human prompt engineer across all of their evaluations in a fraction of the time and effort. So now I'm going to talk about how our MiPro v2 optimizer actually works and how it actually optimizes your multi-stage prompts. And so this is a joint work with other folks at Stanford, at KTH, Basis, and UC Berkeley. So this is a work I've done with my co-first author, Krista Opslong. Just to give a reminder of what our task setting looks like here and what we have to work with, we are given a training input and a validation input, which in the case of a multi-hop retrieval problem is just a bunch of input questions. So this would just be, what is the capital of France? And obviously that's a very simple question, but you can ask things that require you to retrieve over multiple documents. And we just need the inputs. We don't necessarily need labels unless our metric requires labels. So if you're using exact match accuracy or something like that, then you will need labels. But if you can have an LLM as a judge that doesn't require you to have labeled outputs, that's fine. All you need is your input data. Then you also have your language model program, which I showed how we wrote it earlier. And this is the cartoon version that I mentioned would come back. And then we have a metric, so exact match accuracy, or blue score, or rouge score, or LLM as a judge, or even human evaluators, although we make many calls to your metric, so we're working on bringing humans into the loop a little bit more efficiently. And what we're trying to find are optimized prompts for all of your language model calls. So to remind you what this looks like, something like this, where we found both a better instruction and better few-shot demonstrations that will optimize the entire system's performance end-to-end. So we want to find the instructions and the few-shot examples. And another thing we do is assume no access to log probabilities or intermediate labels, and this enables people to use DSPy with closed weight models and API access only, and with minimal data. So there's very interesting prompt optimization techniques that do use access to log probabilities, and they should theoretically work fine in DSPy, but we just make this assumption so that it works with every model. So the key challenges here are both prompt proposal and credit assignment. Prompt proposal is tricky because searching over all the possible strings that we could use as instructions is quite intractable, especially for multi-stage programs. But even a single prompt, trying every possible character string would just be very difficult or impossible. And then credit assignment is also a challenge because when we're changing, say, we maybe have 20 prompts that we're trying to optimize, even fewer is still quite difficult, but if we want to swap out like 10 prompts at a time, how do we know if swapping this prompt actually changed the performance of our system, or if it was the other prompt that we switched? So we have an interesting Bayesian optimization we do to do this credit assignment. But MiPro v2 works in 3 steps. First, it bootstraps task demonstrations. Second, it proposes instruction candidates with a language model program. And finally, it jointly optimizes over these candidates that it's proposed using a Bayesian learning algorithm. And that's how we do the credit assignment. So first of all, bootstrapping the task demonstrations. So given our setting here, we have our inputs and we're going to run them through our program. So we'll generate a search query, we'll generate a second search query, and finally we'll generate our answer. And we will pass that to the metrics. So let's say we're doing a multi-hop retrieval and it's exact match accuracy. We find that this answer was not correct. Then we discard this run through of the program. And we'll try again. So we might reuse the same input because language models are stochastic, or we'll try a different input. And we'll run it through your program, generate the search queries and answer outputs, and then run it through our metric. And finally, maybe this time it actually did work. So here we'll say this is a task demonstration candidate that we will keep and try to put in your prompt later. So for example, it'll look like something like this. And I think a key insight is that we're actually bootstrapping this rationale too, which a lot of other prompt engineering tools, or if you're doing manual prompt engineering, a lot of times people won't think to include this. They'll think to include my inputs and my outputs, but including this rationale actually is a way of showing the language model how to think about the problem. I think that's actually really powerful too, because we are showing it how to do its chain of thought as well. And so now step 2 is proposing the instruction candidates. And the way we do this, the key insight is that we want to ground an understanding of your task into the instruction proposal. So we make your instruction proposal program aware by showing the code, your DSPy program, to a language model and asking it to write a summary. So it might write something like, this task is particularly about answering questions from a given context. It uses language models to generate search queries and answers. We'll make it data aware. So we'll take your data set, your training inputs, and show it to a language model and ask it to write a summary. And so it might say the data set contains trivia style questions from a wide range of topics such as music, film, literature. We'll take the bootstrapped demonstrations that we just created and show those to the language model too as an example of your task working as expected. And we'll also put the prompt engineering tips that you're all familiar with to try to eke out that last bit of performance. Things like don't be afraid to be creative, include a high stakes scenario, provide the language model with a persona. So things of that nature that help a prompt kind of like push a few extra percentage points of performance. And we'll take all of that and we'll show it to a language model. And it will generate instruction candidates for us. So here are examples of instructions that have been generated by this language model program. And you could see it's kind of just different ways of saying the same thing because we don't necessarily know what's going to work for one language model or another. So we have to try out a bunch of different things and we seed it in an understanding of your task to hopefully get higher quality candidates to try. And finally, we're going to optimize the combination of both. So the key idea here is that MePro uses a Bayesian surrogate model for credit assignment. And if you happen to know a lot about Bayesian optimization behind the scenes, we use a structured tree parsin estimator, but that isn't super important to what we do. The high level is what we do is sample different combinations of instructions and demonstrations and update our belief that a given pair is good. Or that actually given each independent variable is good. But because we're sampling multiple, you'll eventually get beliefs over the joint set. So we're going to explore combinations of instructions and demos on many batches of your training data. So we'll sample demo set 1 and instruction 3. And let's say that worked well. Now I update my belief that each of those independently is good. And I sample another set here and that one was bad. So I update my belief and say that these are potentially bad. And I keep sampling, and over time, I'll be sampling multiple combinations, and every few mini batches, I'll run a promising pair of candidates or a promising set of candidates on your full training set. And finally, I'll ultimately select the combination which scores highest on your validation set. So this is sort of a more efficient search process using this Bayesian learning algorithm to try to do this credit assignment of what's actually good and what's bad without having to just change one thing at a time, which would be intractable for these multi-stage programs. So how well does an optimizer like MePro v2 work? Well, we have our benchmark LangProbe, which stands for Language Model Program Benchmark, which is a still growing benchmark, but here we have 6 tasks, some multi-hop QA, classification, natural language inference tasks, and we have some results here. So first of all, we optimize just your instructions and see how that works. And the takeaway here is that optimizing instructions will deliver some gains over just using the templated signatures. And the grounding does seem to help. But then we will optimize your few shot demonstrations. And here we're just optimizing the few shot demonstrations, no optimization of instructions. And what you see is that optimizing these bootstrap demonstrations is really key. This always leads to these performance gains over the default signature. And an interesting thing, a little aside here, is that there isn't a clear pattern as to what makes a good few shot example. So you can see this plot is showing over time we've tried sampling different few shot demonstrations. And it really is just a few cases of really high performing things to put in your prompt that boost your performance above everything else. So really understanding which few shot demonstrations to select right now is a very random search process, or we do use Bayesian search too. But understanding and being able to select ahead of time what makes a good few shot example is an exciting area for future research. And finally, we have MiPro, which is the combination of optimizing both your instructions and your demonstrations. And on almost all of our tasks, we find that optimizing both the instructions and the demonstrations is most effective. And also, we find that the impact of optimizing the instructions rather than the few-shot demonstrations is more visible on these tasks with several isolated conditional variables that you can kind of put into rules in the instruction. In the interest of time, I won't go into too much detail with this finding, but it is interesting that there's a distinction that makes instruction optimization potentially work better on some tasks. So our key lessons. Natural language programming. So programs can be more accurate, controllable, transparent, and even more efficient than models. And you just need these declarative programs, not the implementation details. And what you can use are high-level optimizers to bootstrap your prompts, modify your weights, or deal with whatever the next paradigm is. So basically what we're trying to say here is instead of focusing on the nitty-gritty details of how do I fine-tune my model to specifically perform really well in this task, think abstractly. I want to rewrite a search query and I want to call to my retrieval engine and I want to answer a question, and then let DSPy or a similar framework work out the details of the prompt engineering for you. So like the rest of computer science, machine learning is finally becoming truly modular. You can write algorithms that directly learn to process your domain's high-level objects, such as questions, and not these machine learning specific parameters. And so I'll skip through this impact, but there's been some coverage on our work, and it's really helped out some startups who are working on like different red teaming of language models. And I'll close with, if you want to learn more about DSPy optimizers, here are the links to check out. So we have a tutorial on how to get started with DSPy. We have a notebook on how to get started with MiPro v2 optimizers. And if you're really interested in the details, you can talk to me or check out our paper on archive, which was recently accepted to EMNLP as well. So is this the path to AGI? Well, Omar, the creator of DSPy, certainly believes it's the path to artificial programmable intelligence. And I will say, I do actually think that some of the stuff that's coming out recently with O1 has to do with bootstrapping reasoning and fine-tuning on that, which is very similar to what we do in DSPy, where we generate a bunch of outputs, keep the ones that work well, and we show that reasoning in the prompts. I think that that is a significant factor in what OpenAI is doing with O1. So thanks, everybody, and I think we have a few minutes for questions, potentially.
Yep, thank you so much, Michael. Really exciting talk, and I really love what DSPy does to thinking about problems. So yeah, let's jump straight to questions. Yes?
So I was wondering, how does this compare with TextGrad?
Yeah, this is a great question. So we've actually implemented similar benchmarks to, or similar methods to how TextGrad works internally in DSPy, where essentially we will generate a bunch of answers, look at ones that work, or look at ones that don't work, use a language model to say what's different, and ask it, now update my prompt to work better. So I'll say two things that are somewhat different from TextGrad. One is like we've implemented TextGrad, and on our internal benchmarks, our method was slightly different than TextGrad, but we weren't seeing super large performance gains, or really we were seeing that the MiPro optimizer was still doing better than doing this. And I think the key difference is that TextGrad is doing a local search. So given a prompt, we're trying to make that particular prompt better. Whereas what MiPro is doing is proposing casting a very wide net. We're trying out all of these different instructions that maybe have no relation to one another besides the grounding in your task, and we're searching over those combinations. And I think as it stands right now, that's a better strategy. However, I think stacking those together is also an exciting direction where we could maybe start with a global search and we try out a bunch of things and then zero in on a local, this prompt is working pretty well, so how can we tweak that prompt to make it slightly better now? But yeah, that's a good question. Yes, I would start with MiPro and then run TextGrad on top of that.
Thanks very much. Really enjoyed that. A couple of questions. One is just, you guys are choosing to kind of optimize in token space. So you're dealing with discrete optimization problem. You could optimize in the vector space directly. Why don't you, or kind of like, if you do, kind of how does it compare? And a sort of related question, like less specifically about how you optimize, but more just about the user experience. Like one of the downsides, I guess, to kind of going to this paradigm is you go from a very human interpretable natural language interface through to something more structured that looks a lot like code or like PyTorch. One of the things that we've seen work best is have domain experts like really closely involved in prompt engineering. How do you guys kind of bridge that gap? Like how do you get the domain expertise back in?
Sure, yeah. So no, all good. I guess to summarize the two questions, the first one is why not optimize in the like sort of embedding space, and like, and then the second one is how do you bring humans back into it when it's like we're structuring it as code instead of like just kind of plain text prompts. Non-technical folks, yeah. So the first one, we chose not to do the sort of embedding type optimization of prompts, and that way because of, well, I guess two reasons. One is like it doesn't allow you to work with API access only models, such as ChatGPT, and the other reason actually kind of ties into your second question, which is like you end up with prompts that aren't interpretable. So because we're optimizing and we're having language models write the prompts, they end up being prompts that you can still read and understand exactly how this prompt works. Whereas a lot of those sorts of automatic prompt optimizations will end up like with these really weird strings that won't make any sense to a person, and they interestingly do transfer across models, which is kind of interesting in its own way, but and they probably can be slightly better. So we're not opposed to necessarily having an optimizer that does that, but I think there is some benefit to being able to look at a prompt and edit yourself, which goes directly into your next question, where DSPy will allow you to look at the prompts that it's come up with, look at the few shot demonstrations, and tweak them yourself. So I think having a software engineer and a domain expert who maybe is non-technical work together, where the domain expert can say, I think these are the steps we should take to solve the task, let's implement them. And then the software engineer can optimize the prompts and show the prompts to the domain expert and say like, now what do you think about these? Like how can we rewrite them? All of that is something that you can do with DSPy. And we're working on making like a nicer kind of user interface for making that possible too. Yeah, awesome.
Hey, great talks. I had a question about your intuition where the trend is going. So as we're seeing these frontier models become more and more powerful, maybe the exact wording of the prompt is becoming less important. So how do you see kind of this optimization step and the progress of the sort of raw power that these models are giving you?
Yeah, good question. And we are seeing that where the instructions perhaps matter less, but what we haven't yet seen is the demonstrations mattering less. So showing, and I guess a powerful way of putting it is just like show, don't tell seems to work really well. So if you show these larger models exactly how you want them to work and show them the reasoning too, it seems like that is having still benefits even at scale. So I do agree with you. I think like the very specific wording of the instructions may not matter, but I still think finding the optimal demonstrations and especially that step of bootstrapping the reasoning is going to be really key. And I think that I don't see that ever going away personally, because I think if you show a person how to do something, you know, they're going to understand it a lot better than even if you wrote like a 30-page most detailed way of possibly doing something. You just show them a few examples and they'll hopefully do better and be able to follow those examples. So I think at scale, demonstrations are the future.
Right. Thank you so much, Michael. I'm sure we can pick his brain for hours, but yeah.
Thanks, everyone.
Yeah, for the sake of time, let's continue with the next speaker, and yeah, you'll have the coffee break and the after party for this. So the next speaker is Natalia Vasilyeva, who is a VP and Field CTO in machine learning at Cerebra Systems. She has decades of R&D experience in AI fields, including NLP, CV, IR, you name it. And she's a former senior research manager at Hewlett-Packard Labs, leading teams in text, image, and time series analysis. Today, she will discuss trade-offs between training language models from scratch versus adapting existing models for specific domains and languages. And she will mainly address questions like which model size to pick, how much data is required, and how to avoid catastrophic forgetting during adaptation. The floor is yours.
Thank you. Thank you, and hi everyone. I'm really glad to be here. I'm from Cerebrus. At Cerebrus, we build very large processors, and we build powerful AI supercomputers out of those processors and systems that host those processors. And we also train a lot of models on those supercomputers. We train those models for customers, and many projects that we do are about making the models that work really well for some specific languages or specific domains. So we very often met with the task that when we need to build the specialized models. And I want to share some of the experiences and learnings from that process today. So there are many strong models available out there, all of them open, not that open. One of you and many people may ask questions, why do you need a specialized model? Do you actually need one? Counter question is, does that model actually speak your language? And by language, I can mean either a different language, geographical language, or it could be different domain language, medical, chemical, legal, patent. They all have very different language, very different jargon, very different keywords. So that's the model, that open model speaks really well that language or not. And the second question is also the cost, even the first speaker. And I think intuitively you can think that having a very large model that knows everything might be good, but it might be expensive to serve. Would it be better to build a model which is smaller, but it's very specialized and good for your specific task? We are looking into trade-offs between those two options. So when I talk about, even if the large model speaks your language, sometimes it doesn't do that very efficiently. And by not efficiently, I mean also the cost of serving. So if you look at all of their, especially open models, they are built in a very kind of English-centric and general domain-centric way. And that's the way how their vocabularies and tokenizers are built. And what it results in that it essentially discriminates people who wants to use those models for other languages and for other domains. So here I give an example of tokenization for an English sentence and a Japanese sentence. So for Japanese sentence, their Llama tokenizer actually splits every single word into characters. And for some languages where every single character is represented by 2 bytes, because Llama used byte pair encodings, every single character or some characters will be split into 2 tokens. This is really inefficient. It's costly, but it also doesn't allow you to feed into the model as long context as you might want during inference. So downside. This is true not only for just natural languages, it's also true for domain-specific languages. So here a comparison between, again, Llama 2 tokenizer, which is a generic tokenizer, and a special tokenizer built for scientific domain. You see that Llama breaks pretty simple words like molecule lithium and some other very domain-specific chemical notations into multiple tokens. And the tokenizer and vocabulary, which has been built specifically for the domain, doesn't do that. So which results in more efficient tokenization and, again, less expensive serving and ability to feed more context into your model. So it could be that the model, again, doesn't speak your language at all. It could be that it speaks your language, doesn't do that efficiently. So if you need something better, you have 2 options to pass to follow. You can train your own model from scratch, or you can try and adapt an existing very strong model, which already knows a lot about this world, to your domain or to your language. There are multiple pros and cons to both of those approaches. Training your own model from scratch typically is more expensive, requires more data, requires, I would argue, more ML expertise. It's harder to train a new model from scratch than to adapt an existing one. But it potentially can result in a better accuracy on your final downstream task on your target domain in your target language. And it also could result in a model which is more lightweight, which is smaller and cheaper to serve. And adapting from a strong model also may have its advantages. So how do you make an informed decision, and how do you decide which route to go? Because both of those, training from scratch and even language or domain adaptation, actually can be quite expensive and can be comparable in cost, as I will show soon. The answer to this question lies in an ability to run, to prepare, and to make informed decisions based on the many observations that you can collect from small-scale experiments. So in Russian, we have a saying, measure 7 times, cut once. I know that people from this country like to measure twice and cut once. So I think in this case, you need to measure 7, maybe even more times than 7, to really make an informed decision. And we do run tons of small-scale experiments. We do a lot of ablations to finally decide what's the proper production run should be. Coming back to the steps for kind of language and domain adaptation, how the overall pipeline, at least for us, looks like. So typically, we will start with picking baselines and candidate models for adaptation. So we'll pick candidate models and evaluate them. Maybe you don't need even to train a different model. Maybe an existing model does pretty well. Then we will look at vocabularies, and we will look at how good the vocabulary of existing models in representing, how good are they in representing target language or target domain. So we will determine the efficiency of this vocabulary and tokenizer, and we will train a domain-specific or language-specific tokenizer if needed. And then there is the most important step here. We start exploring these options and trade-offs for training, inference, and making a decision what's the final model should be. And for that, we will go into this exercise of training a very large number of small-scale models. We will fit a scaling law, and we will reason what the production run should be. And we will compare that against the baselines. Then once we make a choice, we will run the final production run. Let me walk through one example how we've done that for Arabic language model. First step, again, about vocabularies and tokenizers. We will look at different vocabularies and different tokenizers that can be built for your specific domain, for specific language. The very first step to evaluate the efficiency of the vocabulary, we will look at different things like fertility. We will look at parity across different languages and different domains. We will train small-scale models to evaluate the different vocabularies. Here's an example of a tokenizer that has been designed for Arabic language model, Arabic English language model that we've trained some time ago. When we started the journey, we've started to look at existing vocabularies and look at how good they are in representing Arabic text. And you can see that the vocabulary in English, GPT-2 vocabulary, is pretty good in representing English. So fertility score here is a metric which tells you how much you're breaking down every single word in a sentence. So it's an average number of tokens per word. You can think about that way. So the higher that number is, the above 1, that means that you're breaking more and more words into more and more tokens, and that the representation is not that efficient. So you want that to be as close to 1 as possible. So GPT-2 does pretty nice on English, does terrible on Arabic, and does decent on code, but not that very good. CodeGen, which has specific code vocabulary, does much better on code, does even also good on English, but again, terrible on Arabic. We took a specific Arabic vocabulary from a model that has been trained for that. You can see it does really good or much better on Arabic, not as good on English and code. We looked at Bloom, which is back then was a well-known multilingual model. And we can see that it does average across the board. We train our own vocabulary, our own tokenizer, which actually does really good across all of 3 domains. Again, to evaluate that, the first thing is to look at fertility. Is really cheap exercise to do, but also we run small-scale models with all of those tokenizers and look at upstream losses. You can use new vocabulary if you're going to train your model from scratch. You have this freedom to choosing a completely new vocabulary. If your final choice is to start from an existing model, you cannot just swap the vocabulary. You cannot swap the tokenizer. Then we look at opportunities to extending an existing vocabulary of an existing English-centric model to your new language and to your new domain. So here I'm showing also some exercises which we've done on extending the vocabulary of Llama 2 to Arabic. We've played with several options. We've just looked at what if I take, let's say, 30% of Llama 2 vocabulary, remove 30% of less frequent tokens in English, and replace them with 30% equal amount of high frequency tokens in Arabic. That worked. We see that we improved fertility in Arabic, reduced fertility in English, but English degrades. What if we double the size of the Llama vocabulary? It's not as huge. Llama 2 had only 32K. If we double that and we add the same amount of Arabic tokens there, we actually see the best, much better results. So we further reduce the fertility in Arabic and we keep fertility in English the same. So that's so far has been a really good approach for Arabic. We've experimented with other domains and other languages as well. So usually it's again, you need to try and play and experiment to see which makes sense, which vocabulary size and which scores make sense for you. Once you've done with the extension of the vocabulary, another important step is also to make sure that those new tokens that you add into vocabulary are properly initialized and they are aligned with the previous vocabulary. So we do that through a two-stage approach. First, we carefully initialize them by either, we have two methods. We either pick like average scores from existing multilingual vocabulary that fits our target language and domain, or we do some kind of projection. And I have a link to the paper to talk about that in more details. And then once we initialize them in this thoughtful approach, we also first train the full model with first train embedding only. So we freeze the backbone of the model and train embeddings only. So now we have all of the kind of vocabularies, all of the setups to actually starting choosing what the production run should be and exploring the trade-offs. So how do we do that? We rely a lot, we relied a lot on the scaling laws, and that's exactly what I was afraid of that will happen. So it's supposed to be a straight line between the three data points, and these 3 data points represent 3 sizes of the models. So we start always with training from scratch very small models. Those are supposed to represent, I think, 110 million to 156 million, 590 million parameters. So we train them from scratch. We measure upstream loss, in this case in Arabic, and we fit a scaling law to predict what kind of performance I could expect from a larger model. So the last data point here is the data point for 30 billion parameter model. So that's the expected loss for 30 billion. Its upstream loss still doesn't tell me much about how to compare that with the existing models, which are not trained from scratch. So the gray dots the gray dots on the left, right, are about around 4 and 5 data points corresponds to Llama 2, 7 billion, 13 billion, and 70 billion. And you can see that those small-scale models do much better than much larger models, English models out there. The next thing is to actually train those models for longer and to compare that with small-scale domain-adapted models. I apologize, all of the labels on these figures are gone. And that's exactly what I was afraid of. So the orange dot below corresponds to adapted Llama 70 billion, and green dot above corresponds to 590 million parameter model, which has been trained for a little bit longer. So instead of training that in compute optimal regime with 20 tokens per parameter, we trained it on much more data. And here you can see that in terms of upstream loss, 7 billion model adapted does better, but not by much. This is on upstream loss only. We want also to look at downstream tasks, and the ratio remains. So still 7 billion adapted does a little bit better than 590 million trained from scratch. And now we also can relate on the downstream evaluations of their models, Llama models, just not adapted at all, which are gray dots on the left side. So this allows us to kind of reason what we could expect from either training from scratch or domain adaptation. And at this point, we can make a decision how to proceed. So in this case, we've decided actually that training models from scratch makes sense. And we've trained a large series of models from scratch, starting from 590 million up to 13 billion, and then a larger model, 30 billion parameter model, trained on a much more data. So in upstream loss, you see that everything follows the scaling law and the models behave as expected. If I lay on top of that now domain adapted models, so orange dots here, the leftmost is 7 billion, next is 13 billion and 70 billion. So you can see that the 70 billion model actually does a little bit better than 30 billion trained from scratch. So in terms of cost of serving, you can do 30 billion, which does as good, almost as good as 70 billion adapted Llama. And x-axis here is compute. So the cost of reaching those points is almost the same. So if you care a lot about cost of serving, you would probably choose the train from scratch model. And the same plot, but now with the downstream evaluations. So we see that the ratio, the relative performance of these models remains the same. And here I have my labels back. So you can see where all of the green dots corresponds to models trained from scratch. Orange dots are domain adapted or language adapted are Arabic models, and gray dots are just Llama out of the box. So there is an interesting also thing that in terms of 7 billion parameter budget, you can see that trained from scratch even performs better than 7 billion adapted. 13 billion models perform approximately the same. For 70 billion Llama outperforms 30 billion trained from scratch by a bit. So this gives you hopefully a map to kind of reason in terms of where it makes sense to choose one over another. And another slide has a little more breakdown on downstream evaluations. And you can see that essentially J30 billion, that's a model trained from scratch, is almost on par with 70 billion adapted. So again, in English, 70 billion adapted does better. In Arabic, they are almost on par. So if you kind of give some food for thoughts. So we've experimented with this on top of adaptation of Llama 2. We also looked at adaptation of Llama 3 and found that Llama 3 are actually much harder to adapt than Llama 2. We can hypothesize what's the reason for that. Maybe it's unknown pre-training data distribution and unknown hyperparameters. All the hyperparameters are also not known for Llama 2. So mostly it's a very different data distribution for training Llama 3 compared to Llama 2. We started the first attempts to adapt Llama 3 models for different domains. One of them was making those models better in math and reasoning. We also attempted to adapt Llama 3 to Arabic. And we saw that in both cases, we see degradation either in English or in some of the reasoning tasks. So we got back to the drawing board and looked at kind of what kind of data set we should choose for replay to avoid this catastrophic forgetting, to avoid the degradation of the scores where Llama has been performing well already. So we've done analysis on looking at kind of improvements on specific subsets of the training data as you continuously train from Llama. And that helped us to understand which subsets of their commonly used training data sets correlate the most with the data that has been used to train Llama 3 initially. And then if you use for your replay a larger percentage of data here, then you can avoid catastrophic forgetting. In addition to that, we also looked at different synthetic data sets available out there, because we believe that that also might be better representative of the distribution of the data that has been used to train Llama 3. By running, again, a large number of small-scale experiments, all of that has been done on smaller models. We picked our ideal replay data set, and we were able to kind of fix adaptation of Llama 3. So we arrived at a much better adapted model later on. We run all of those experiments at different scales. For all of that study, I cannot say like hundreds, thousands of small-scale experiments. And we believe that doing that quick loop and experimentation is really important to help you reason and to make the right choices. So you must do all of that. We are running all this on our hardware, which makes it easy to scale the models. And it makes it easy to scale the models because we disaggregate kind of computation resources from memory. It allows us to feed models of any size on a single accelerator, or to run smaller or larger models across large clusters of devices. So no matter what class size of the cluster that you want to train on, you always have the same code. You always have the same hyperparameters. You also always can use exactly the same batch size to train on a single system or on a very large cluster. And also we can do that independently on the model size. So actually, as of a week ago, we successfully ran several iterations on 1 trillion parameter model on a single accelerator. It's slow like hell, but it runs. It allows you to debug things, and it allows you to kind of iterate much quickly on the code. So this enables us to do those scale down, scale up experiments with exactly the same code base really effortlessly. And we believe that ability to do that improves your ability to train high quality models moving forward. And in addition to being efficient in training, recently we've also introduced inference. Now we support inference at the highest tokens per second per user and the lowest latency. That has been fun because we launched the product a few weeks ago, and since then it was already several updates. And we see healthy competition there when every week folks like our competitors like Sampanova, Grok announce higher speeds, and we continue beating them. We plan to continue doing that. interesting times we are living in. So that's an update as of this week. Last week, the graph looked differently in terms of throughput and latency on 70 billion model, and we have the same for 8 billion as well. Why I think that's relevant to the whole conversation about trade-offs, because if you know in advance what kind of hardware you would use for inference, it will also inform, obviously, your choice of the model as you train that. Not only in terms of model architecture, but also what you can afford in terms of sizes, etc. So it's really important to know what you are up to what are the requirements for production. We are capable to do this fast inference, fast training, because again, we have very large processors, which have a lot of on-chip memory. And on-chip memory is that what matters for at least, especially for high throughput and low latency inference. In conclusion, I think large language models are there. They fuel tons of use cases. And we do believe that adapting or creating those specialized models is important. That allows you to have better quality and cheaper in serving models for deployment. There are a couple of ways to do that, either train from scratch or adapt. And you can make informed decisions which path to go if you do this homework of small-scale experimentation and reasoning about what you can get from different model sizes, different data set sizes. So this very meticulous study and plotting of all of the expected losses, etc., is a really important step to guide your large-scale runs. And at Cerebras, we do all experiments, small scale, large scale, on our hardware and find it very easy to use. So answering, I think, Jakob's question, which hardware do you use for runs? And are you a customer of NVIDIA? My answer is no, and we run everything on Cerebras. Thank you.
Thank you so much. It was a great talk. Do we have any questions from the room? Yes.
So comparing NVIDIA GPU versus Cerebras big chip, how is the performance? So both train on Llama 3 70B, what's your benefit?
Sorry, what is what?
Comparing Cerebras chip versus NVIDIA GPU on full training or on the fine tuning and on inference, what's your benefit? What's your advantage against NVIDIA's?
We require much less processors for training, and it's much easier to do so. It's much easier to train because you don't need to worry about distributed setups. So we would train a 70 billion model on just a few systems, and the code will look like it is for a single device versus very large-scale clusters on GPUs. And for inference, I think it's even more fundamental because we have much higher memory on chip, which is SRAM, very high bandwidth, low latency. It allows us to feed the whole model into SRAM, and it allows us to produce, to serve the model at speeds which are not feasible on no matter how many GPUs you try to put.
So you showed that you used adapters as well for the language models for fine-tuning. Which type of adapters were you using? For example, if you were using LoRa, what were the hyperparameters and what was their impact?
Yeah, for language modeling, our conclusion adapters don't work. We looked into that. So we looked at, that was a question essentially when we started looking at the language adaptation. One of the questions was, okay, maybe it's enough just to fine tune the model. The answer is no, especially coming back to the whole reasoning about vocabularies and tokenizers. You want to expand the vocabulary usually, and then you need to train your model. You need to train new embeddings for those tokens. You could do that. You can still use kind of LoRa approach and Solar approach, which is another way to kind of freeze part of the backbones and add additional layers together with new embeddings. But specifically, LoRa doesn't work well. I think LoRa might be okay when you need just to address new tasks. But if you want to change completely the domain or language of the model, it's not enough. So full fine-tuning is much better.
Quick question. Can you speak to the costs, relative to NVIDIA, right? And you spoke about latency, you spoke about throughput, right? And how are you in terms of price?
For inference, if you compare our costs versus costs on any NVIDIA-based API inference API providers. I think we are, I think, up to 5 times cheaper. For training, I would say probably on par, but it gives you it's much easier to run, and it's much easier to support because you have less units. So it's like you're trying to do work with a few bulls instead of, I don't know, hundreds of chickens.
Right, I think we'll have to wrap it up for now, but feel free to discuss over the lunch break. So thank you once again.
Thank you.
So our third speaker for this session is none other than Douwe, who is the CEO of Contextual AI and an adjunct professor in symbolic systems at Stanford University. And also he's a former head of research at Hugging Face and a research scientist at Facebook AI Research. He works on grounded AI models, multi-agent systems, and retrieval augmented language understanding. And fun fact, he's the author of the original V0, or however you want to call it, retrieval augmented generation paper. Also, another fun fact is that he was also last year on our annual conference, and he gave a talk at 7 a.m. local time, so thank you for that. But this year, he will cover 2 research contributions that came in the past 12 months from Contextual AI, namely GRIT, which stands for Generative Representational Instruction Tuning, and OLMO. So, Douwe, the floor is yours.
Thank you. Hi, folks. Yeah, so thanks for coming all the way to Berkeley for this. I had to come all the way from Palo Alto. I didn't expect it to be this far, this event. So thanks also to the Zeta Alpha folks for inviting me here and giving me the opportunity to give a technical talk. Those are quite rare for me these days. I mostly do sales pitches. So I made a brand new talk just for you to talk about doing RAG on the edge. So I should say that most of this work I had very little to do with. This was mostly done by the amazing Nicholas Munichhoff. He works at Contextual. He's starting his PhD at Stanford. Really amazing researcher, and he did all of this work. I'm just kind of the conduit to tell you about it. So why do we want to bring AI to the edge? So by the edge, I mean your phone or kind of IoT settings or in vehicles or anywhere else. And so the obvious answer is that if you can run things locally, that means that your data doesn't have to go somewhere else, right? So that means that you can do RAG on the data that's on your phone without, or that you can do AI on the data that's on your phone without having to reveal that data to anybody else. So how would you do that? Through RAG, kind of obviously, I think, at this point. So does everybody know what RAG is? Okay. Should I explain it for anyone in the room? I'm not sure. Technical audience, right? Yeah, I was wondering that too. This is version 1, right? But yeah, so the basic idea of RAG, right, is that you have a language model and you make it work on other data. The way you do that is through retrieval, and you use the information that you retrieve to contextualize the language model properly so that it can do its job, right? So this idea has become pretty popular, especially this year, I think, for just making Gen AI work on your data. So what I'm going to be talking to you about here is how can we make RAG systems efficient enough for them to be served up on edge devices. So there are 2 papers that kind of cover different aspects of this. One is GRIT, Generative Representational Instruction Tuning, where the main question we answer is, can we use just one model for both the generation and the retrieval? So that's one. The second one I'm going to talk to you about is OLMO-E. You might have heard of OLMO. So this is in collaboration with the Allen Institute for AI. And this is the mixture of experts version of that. So mixture of experts has a couple of very nice properties, and one of them is that you can do inference very efficiently. So what we did here is build a fully open source mixture of expert model that is best in class. And then I'll just close out with some closing thoughts. As you notice in the slide, there are lots of acronyms in general in the field. My VP marketing is always very annoyed with me for using so many acronyms, but I think to this audience, most of the acronyms will be pretty familiar, hopefully. All right, so starting off with GRIT, this is a collaboration between us at Contextual AI and some amazing folks at Hong Kong University and Microsoft Research. And the basic idea is just to look at these two different paradigms that exist when you're building a RAG system, or in general, when you're doing interesting things with AI, right? So one is this generation part of the system where you just have some input and you want to generate autoregressively some output. And then there's this other paradigm where we take some input and now we encode it into a vector, and we want to be able to just do some sort of non-parametric distance computation so that we can actually find the most similar things, right? Or whatever the distance metric is. So computing similarity between a bunch of vectors. So these are traditionally very different problems, and they are handled by very different models. So wouldn't it be cool if we could unify these two paradigms into one single model that does both things? So why this is a good idea is for a couple of different reasons. One is that you might be able to get better accuracy on both the different tasks because you have sort of a multi-view of the problem, right? So you have to learn different things, and so those two things might be complementary, which means that you might get overall higher accuracy. You also see more data with the same model. So that's one. The other is that you get improved efficiency. So if you can reuse a bunch of this compute, then you might be able to serve these systems up much more efficiently. And the last one is just that from an endpoint perspective, this is pretty elegant, right? You don't need to have different models. You just have one model and it does everything. So you can collapse it all maybe into one single API endpoint if you wanted to. So yeah, this is basically what we did in this paper, GRIT. We unified these two different aspects, and the specific way we did that unification is through instruction tuning. So you're probably all very familiar with instruction tuning, right? So you give an instruction, in this case, when you're trying to learn the representation along the lines of given this and that, encode this information so that I can retrieve the relevant document, right? So retrieval just becomes another instruction paradigm inside this bigger sort of generative model. And then obviously with the same model, you're also generating just like the way you would normally do with a normal language model. So a bit more in the technical details. Jakob asked for some formulas on the slide. So here you go. No, he didn't. So during the retrieval side of this, right, what you ideally want to do when you have a embedding model is you want to have bidirectional attention, right? So sort of like standard BERT or whatever. You want to be able to attend in both directions because then you get the richest representation so that you can do your computation of your distance metric. So the way you would train that in this case is you have this instruction. So something along the lines of, okay, this is the user, here's the instruction. You should be embedding this. So that's the token that you pass to the model so that it knows that it needs to learn to give the right representation. And then you just train this using a standard contrastive loss, right? So that's what that formula is. It's just saying, okay, this document and this query where you know that they are the right pair, they need to be ranked closer. So the distance needs to be closer than for all the other negatives, right? So really standard contrastive loss. On the generation side, that's basically standard negative log likelihood. You're just doing instruction fine tuning, right? So kind of the standard that you would expect here. And then in GRIT, we combine those two losses, and that gives you a GRIT language model. So how does that work? It turns out that it works pretty well, as you can see here. So on the left, you can see the average performance on a whole bunch of different benchmarks for the GRIT model when you compare it to either only training the generation side or only training the embedding side, or comparing that to a bunch of different baselines that were prevalent at the time when this paper came out. As you know, AI moves very quickly, so there's a lot of other models out there these days. But when this came out, this had the state of the art both on the embedding side and on the retrieval side with one single model. So as you can see, there's a lot of very good models on the embedding side, but they're only good at embedding. They can't really do generation. And vice versa, those generation models are not great at embedding. But with GRIT, you can do both at the same time. So it gives you a good model, but you can also do something else with this now, which I think is pretty cool, because when you think about what you're actually doing with RAG, is you're encoding the query twice, right? So let's say you get some question like, what is the capital of the Netherlands or something? Now you need to go and search. So you need to encode that query and then find the relevant document that contains the answer. And then you need to re-encode that query for the language model, right? And you do the same thing for the document as well. So that's not very efficient. Because with Grid, we have the same model handling both, you can actually cache the query, right? So if you do that, you only have to encode the query once. You reuse that compute when you're doing the generation because it's the same model, and you benefit quite a lot from having that cache, right? And you can do the same thing actually with not just the query, but also with the document, right? So you're folding all of this into one single model, and that gives you the ability to cache all of this. So you don't have to encode the document twice, you don't have to encode the query twice, it's all just there. So when you do this, you can see pretty substantial efficiency gains, especially when you go to longer lengths, right? So the longer the length of this gets, as you know, like transformers don't really scale very nicely in sequence length. So then you start really seeing massive benefits here. So in this plot, the sort of black and gray lines, they're just a traditional RAG system that you would normally have. And as the length goes up, this becomes very, very slow. But with Grid, because you can cache all of that compute, you just stay flat. So you get a much more efficient system. So that was Grid. I guess we're not doing sort of interactive. So if you have any questions on that, save them for the end. We can go back to that. So next thing for me to talk about is OMOE. As I said, this is a collaboration with the Allen Institute for AI. Some really amazing people on this paper. And as I said, yeah, the main goal of this work was just to see how far can we go building a state-of-the-art mixture of experts model that is fully open source. So everybody here probably knows a little bit about mixture of experts, but just to refresh your memory, on the left here, you just have a standard sort of dense layer, right? So you would just do your normal transformer forward pass. But what you can do with mixture of experts is essentially find a route through the feed forward part of this, which means that you can use a lot less compute. So during training time, you're still passing through all of these parameters, right? But during inference, you only have a small subset of that, which is your active set of parameters, right? So in this case, we're training 7 billion parameters, but during inference, it's only 1 billion active parameters because we're routing through to the different blocks as we go through the network. So in this paper, we kind of just look at how this compared to the standard approach, right? So if you just look at what OLMO, the original sort of dense language model does, and if you compare that to OLMO-E, what we found here, what these plots show, I don't know if you can see them in the back, but you can get to the same result with about 3 times less flops or token throughput, which is amazing, right? That's like mixture of experts models just are much more training data efficient. And they're also twice as fast. So my takeaway when I saw this plot was basically that we should all just be training MOE models for everything that we do because they're faster to train and they actually end up in a better point. So that's kind of what you're seeing here on the right is that on MMOU, for example, with a model that has the same number of active parameters, the same number of total parameters, but only 1 billion active parameters, it actually learns faster, way faster, right? That line goes up very steeply, and you get to a higher point as well. So it's sort of best of everything. We should all be doing MOE if we can. So looking a bit more closely at the actual results of this, and I would encourage you to just take a look at the paper. I think it's really an incredible paper. It has like 32 different ablations in there, lots of details on like small specific parts of the loss function that you want to use, and lots of other really good nuggets in there. But the main takeaway is just that this is the state of the art for this particular parameter size. So if you need a model and you cannot go higher than 1 billion parameters, you want to use this model. We've also fine-tuned this model, so doing sort of your standard instruction fine-tuning on top of this using DPO and KTO and other sort of alignment methods. You can see that this model also works really well when you have the instruction fine-tuned version, right? So normally when you release a language model, you have sort of your pre-trained version and your instruction version, and so both of these are available, and they're both very, very good. What I think is the most interesting about this is, so this is not like the global state of the art, obviously, right? It's the state of the art at the Pareto frontier. And the particular Pareto frontier that we're looking at here is sort of performance and cost, right? So how expensive is this to actually sort of serve up? And then I guess one of the other axes that we're looking at here is openness, right? So what we did with this model is we released the model, we released the data that the model is trained on, the code to train this model yourself, all the logs, a bunch of checkpoints so you can really evaluate for yourself what's the behavior like over time. Everything is completely open for you to play with and hopefully learn from. So a couple of closing thoughts for me. Oh, I updated this slide, but this is kind of an older deck, I guess. But so where will this go? If you think about sort of RAG on the edge, right? What's the future? I think it's pretty clear that the future is that we're going to have sort of multimodal, multilingual, multitask sort of RAG systems on your phone that are just going to be doing a lot of edge compute. Right? So none of that data is really going to a data center anymore. It's just going to be on the edge device, and that will help you protect your privacy. But if we wanted to serve it up on the cloud, that would also be much more cost efficient, right? So if you take these things I showed you, like Grid and OMOE, if you combine all of this and you were to serve this up on edge, you can serve it up much more cheaply and with much lower latency. So even on the cloud, there are clear benefits to this. I think for me, one of the interesting observations, maybe even over just the past like couple of weeks, is that there's a difference between thinking about AI from the systems perspective or from the models perspective, right? And a lot of us have, I think, been a little bit too obsessed with the models and not really thinking about the systems, right? So if you look at Michael's talk about DSPy, that's also about how do you build a system, right? How do you get these different model components to work together so that that system actually solves a problem? And I think we're doing a similar thing here with Grid, where we're basically compressing all of this system into one single model. And if you think about what OpenAI is doing with O1, it's kind of very similar, right? We're just compressing these rollouts through basic RL back into the language model. So those are my closing thoughts. Hopefully soon we'll have a Grid with OMOE, because you can obviously combine those two ideas, which would be pretty fun. But unfortunately, Nicholas didn't have time to do that before this talk, so sorry. And that's all I had. Thank you. So please follow Contextual on Twitter. Nicholas, that's not his correct Twitter handle. It's just Munichhof. You can find me on Twitter too. And at Contextual, we're hiring. So if you're interested in working on cutting edge RAG on the edge or elsewhere, then yeah, please come talk to me here. Thank you.
Really great talk. I see we have questions already, so let's hop in.
Where am I looking?
Thank you for the talk. I like the idea of combining the embedding and generation together. However, we all know that the generation is kind of like theoretically conditioned on the embedding. Conditioned on the retrieval material from the embedding part. So I was wondering, when you jointly optimize both the embedding part and the generation capability, did you observe any like unstable or any issues?
I'm not sure I really understand your question. So you're saying that generation is autoregressive, sort of from left to right? Is that the point you're making?
The results you get from the generation is sort of conditioned on the retrieved material.
But it's not, right? So in a normal RAG system, you would just, so it's not actually conditioned on the retrieved content, it's just conditioned on whatever came before it, right?
Yeah, I mean, in a RAG, scenario, when you have the retrieve material and you want to, do generation on top of the retrieve material. Now, it seems like that, theoretically, the generation process is sort of like, it has something to do with the embedding quality that you get. So these two, things are not completely independent. So I was wondering, did you observe any issues when you try to optimize for both embedding and the generation capability of the same model?
Okay, yeah, so I still don't really understand why theoretically that would lead to sort of instability. But to answer the question, yeah, we didn't really see any instability. What we're basically trying to do is fold it all into the same paradigm, which is instruction tuning, right? So we're turning the representation into a part of the instruction set. And so when you do that and you jointly train on this data, then yeah, you sort of get best of both worlds.
Sure. Thank you.
Any other? Yep.
What's your inclination on state-space models? How do they fit into all of this, given that state-space models could also run locally?
Yeah, every model in theory can run locally if you make it small enough. But so state-space models, I think is very exciting. There's a lot of cool work happening there. I always kind of, when I'm on like panels and stuff and people ask me about the transformer and why it's so special in the seminal Google paper, I always tell people that the transformers aren't really that special, right? It's just that we have GPUs and transformers happen to be very good at running on GPUs. And that's why they're the popular paradigm, right? What is really working here is just lots and lots of compute and data that we can use to train these models. So I think state-space models are very interesting. The thing I haven't really seen is like a real like production grade sort of differentiated model that is clearly better than a transformer. I think once that emerges, then a lot of people will just move straight over.
Thanks. I see more questions and we have some time. So
thank you. Great talk. I have a question also about this combined retriever plus generator and related to the, again, this idea of domain and language specialization. What we've seen in our work then, especially the quality of retriever is really important. And the general models are really not that good in retrieving the right context if you are talking about specialized domains, and which makes sense because if you think about representation, just the whole space, all of their like the medical domain will be bumped into some narrow space. So what we do internally, we usually kind of, again, fine tune those embedding models, and then pretty frequently can still reuse the general generator without any changes. So if you use the same model, doesn't mean that you always, and also embedding models are usually much, much lighter and much, much cheaper to train. So can you comment on that and what are your thoughts?
Yeah, so I think what you're saying is that just embedding models inherently, if they're general, they're not very good at anything in particular, right? I think so Zeta Alpha is making a business out of that in a way, right? And so are we actually at Contextual, and so are you, it sounds like. I think, so the underlying problem there is that a contrastive loss when you train it on general data is just going to learn semantic similarity. And semantic similarity is not what language models need, right? They need semantic relevance for answering the question correctly. So at Contextual, that's why we're working on things like RAG 2.0, which you might have also seen come by, where we're actually backpropping into the retriever mechanism when we're training the RAG system. So when you do that, then you get semantic relevance out of your retriever, which means that it's much better for any sort of RAG task, right? And then, so the kind of specialization that you want to do, I think you want to do it for your entire system. There's no reason why you would only do it for the retriever. It's just that that's easier, or sometimes you have
it's
a
less
GPT-4
expensive.
model.
I think, yeah, the main reason to do that is because to do this adaptation for retriever only, it's very cheap.
Yeah.
But if you use the giant model, which is used for generation, it's much more expensive to adapt.
Yeah, but so I think there are also lots of like production deployments that we see where there actually are no embeddings anymore. So it's sparse retrieval with a re-ranker, and that re-ranker is very cheap to train. So it just depends.
great. Thank you once again. So let's wrap up this talk. So thanks again, once again, Kiela.
Thank you.
And so we have a very short coffee break, just for 5 minutes or so. So we can come back to the third and final session, where we'll have 2 more talks and a panel discussion. So feel free to go back to the speakers and ask them more questions, or enjoy the coffee and the demos. Thank you. Hello, hello. Let's slowly get back to our seats so we can wrap up with the third and final session. All right. Okay, welcome back, everyone. So this is going to be our third and final session, which is going to be 2 talks and 1 panel discussion with all of the speakers. So without further ado, let me introduce to you the 7th speaker of the day, which is none other than Fernando. And I know Fernando because he's the CTO at Zeta Alpha and has a PhD in theoretical physics. Today, he will discuss RAGOps and its role in optimizing generative AI deployments with a goal of having high accuracy and return on investment. So we will cover details like data integration, access control, domain-specific fine-tuning, and other retrieval strategies. And he will also introduce our latest open source tool for developing, testing, and monitoring RAG agents in a framework-agnostic manner. So give it up for Fernando.
Hi, everyone. Thanks for sticking around. We're very close to the after party, so hang on. Yeah, so every single Fortune 500 company nowadays is doing something with RAG. And it starts very easy. You just have your laptop, you install LangChain, and you start coding. But when it's time to go to production, then things start to become more complex. So companies, to overcome these challenges, they start building from scratch a platform to allow them to customize this RAG platform for their own use case. So in line with the trend of appending ops to every operation term, here I'm defining RAGOps. So RAGOps encapsulates kind of practices for productionizing RAG applications. But if you read about RAG on the internet, RAG just 5 lines of code, right? This is what you see. However, what does it take to actually go from a POC to production? Well, first you need to synchronize with your data sources, maybe in real time. Every document has different file format and then maybe a different way of extracting the information that you require. So you need to have different strategies for each of them. Security is also very important, right? So you want to propagate access rights from the source all the way to the retrieval part. So you make sure that people have access to the right thing. Also, extracting metadata is important because it can enhance the retrieval quality. For example, you might be able to filter by certain fields that are important in your documents. Also, you need to decide about vectorization strategies, right? Like, for example, how do you do the chunking of the text? Is it short chunks, bigger chunks? Is the whole page, or other strategies that might discuss later? Okay, so but now you need to improve the performance, right? So you might need to maybe fine-tune the embedded model or select one that is appropriate to your domain and your task. As data accumulates, you also need to scale your pipeline, otherwise you might have bottlenecks. You also need to choose the index technology, right? So as data you might have a constraint. For example, you need far filters, or maybe what about the size? Can you store the vectors within your budget in RAM? Right, this is something we need to consider. Sometimes the information that is in one document is not enough. So you might benefit from integrating with external services to enhance the existing information for each document. As you get more documents, of course, you need to scale the index and then somehow maintain the performance. Okay, now you have this very complex thing. You need to deploy it. Okay, are you going to use Kubernetes or serverless or something like this? Of course, your users will need to interact with the solution, so you might need some sort of front end. You need to think about UX. Is it just a chat API, or sorry, chat interface or something else? You also want to continuously monitor the entire process, right, to ensure the quality of service, as well as to catch all of the issues that user might encounter when they are using your application, as well to incorporate user feedback for later refining of the system. You also need to test and evaluate your quality of both the retrieval and the generation part. And to improve that, you might need to add both domain fine-tuning of the embedding model, or adding a re-ranker, or fine-tuning a re-ranker, or hybrid. You know, it's you can have a lot of things there to improve the quality. Of course, you want to ensure that every user has access securely via SSO. You're probably now managing multiple use cases, right? So you need multi-tenancy now, and then to have some sort of data isolation as well. And of course, you want to get your users to manage and onboard new use case in a simple way without having to do engineering work every time. Yeah, so you see it's a bit more complex, right? This is the kind of what I call RAGOps. So how do we do it as Zeta Alpha? Well, so we have a data ingestion pipeline, and this is all configurable, right? So we have like built-in connectors, but it's also very simple to create your own and hook into the ingestion, as well as to do the processing. Maybe you have a specific file type that is very esoteric. It's also very easy to just build it and then hook it into the existing pipeline. Access rights is also very important. It's enforced all the way through the process. We can combine, the search API can combine multiple strategies. Again, you can also decide what you need. You want maybe a ranker or not, depends on your need. And we can also customize the agents building via the new SDK that Dinos mentioned, which I'll talk about later. And finally, this is like a multi-tenant environment. So you can just grab this, change some JSON file, and JSON API, and then you have a new complete fresh index to work with. We can also deploy it as a SaaS or like on-prem. All right, so what can we do? What can we change about RAG? So let's first look at the ingestion workflow. So you have a document, and then you might need to do different things with document. Maybe you need to extract the images because you want to do a multimodal search, or you want to extract the text part and the layout, because the layout, the layout could tell you how to chunk the text, right? Or maybe not, because there is this new cool paper called Pali, which actually looks at the image of the quadrants of the page, and then from there infers the documents, the embedding vectors. Right, but you need this flexibility, right? Because new things are coming up every day, and then if you're stuck with the old ways, now your quality might suffer. So you might also want to extract extra metadata, right? And this is very easy these days with LLMs. You can just feed the document to LLM and ask, okay, please highlight all of the words that are within my interest. As well as plug extra sources and connect that to the existing document. And finally, you want to index. So all of these things you need to change, right? Otherwise, you will not satisfy all of the use cases. On the retrieval side, it's also a bit more complicated than just templating the top 5 documents into the prompt. Usually you want the LLM to decide on which tool to use, right? Maybe you need to do retrieval or something else. Then that tool needs to call, for example, in this case, a retrieval. But for example, you might want to combine neural search and keyword because you know that some use cases require exact matches. And then you need to fuse those via some strategy, maybe at a re-ranking step at the end, and then feed that back, right? But you can also take the same query and feed it to an external service because you know it works well for certain use case. So now I want to show you some of these examples in action. So this is a very simple virtual assistant, which you probably have built already. So the user gives a question, retrieves top 10 passages, feed that into GPT, and then give the answer. The problem is that in this situation, the users were having very complicated queries that included this huge product ID. And the product ID is like encodes some sort of configurability of the actual product. And of course, neural search didn't know what to do with this, and keyword is also a bit complicated. But what we decided to do is that the company had an actually very cool API that could resolve from this ID, exactly the product that we need. So we combine that as a filter. Then we pass the rest of the query for KNN, but only restricted to these documents. And now we have the exact answers. Another case could be something like a needle in the haystack problem where you want to work with a single document, but maybe this document is 500 pages long. And you want the LLM to find where exactly this section of the document is that you need to extract some information from. And then from there, infer what retrieval you need to do to then answer the question. It could also be that the answer doesn't exist in a single document. In this case, for example, we might need to find the answer from different documents, but we don't know beforehand how to filter those. Right? So we want the LLM to actually decide dynamically how to do it. So in this case, we take a simple RAG fusion approach where you create 3 extra queries based on the original one, but now you need to evaluate these documents that were retrieved using Ragilo, which is I will talk about later, to know which documents are relevant, then feed that to LLM, but then ask it whether it's missing something, right? And then you repeat that process again until you find the actual answer from multiple documents. Okay, so now we have a system that we can customize to our use cases, but how do we improve the quality? So one way of doing that is to fine-tune embedding. So fine-tuning the embeddings is, well, in abstract ways, very simple. So you want to train the model to so that the query that you embed is closer to the correct documents, but far from the incorrect documents. As a secondary objective, you also want it to understand the terminology. For example, if you're a very specific scientific domain like chemistry, the words have different meaning than in normal life. So for that, we use this process called inparse. So we fine-tune the model based on the user's data by doing some synthetic tricks. So basically, we create the queries based on documents, and then there is some hard negative mining that we need to do. We feed that to some base model, for example, multilingual E5. How we decide the model depends on the use case. In this case, it was because we needed multilingual, and E5 is also very small and fast to run. And then you need to serve it. And we found that this method substantially improves the quality over the non-fine-tuned models. If you want to learn more, this is an open source package to do this entire process called inparse. But okay, now if you look at the MTab leaderboard, which is where you can see how different models perform for different tasks, you will find that this is dominated by large language models that were converted into embeddings. So we wanted to, figure out whether it is possible to then fine-tune on top of those to align with, for example, a domain-specific case. But so right now we took E5 Mistral 7B, which is already an embedding model based on Mistral. We combined a data set mix that we created. We took some inspiration from existing papers. And then with only 80 hours of A100s, where we found like, okay, we have like position 8 in the leaderboard. Okay, it's not too bad, but this is not the point, right? The point is that this process works. And if you want to read more about how we did it, we are open sourcing everything, the data set and the entire process, because we want to give back to the community, since we also take this to do our own domain fine-tuning. Of course, these models are not very practical because they are huge and very hard to run, right? You need A100s, but okay, this is the first step. So if we use the smaller models, well, as we typically do, we can see that when we train on domain-specific data, it does improve. So in this case, for example, it's a chemistry domain, and we see that from the baseline, the E5 model improves quite a lot, and then by fine-tuning on the data, we see a lot of improvement, especially in German. And then, we need to add more tricks, right? The point of this plot is that you need more tricks. For example, you need to add a re-ranker and then fine-tune a re-ranker and maybe add a hybrid retrieval at the end. We also tried with other other domains where maybe you don't have query document pairs, but you have, in this case, HR. We had like the CV of the candidate and the job post. And we also see that it works, as well as other domains like legal. Okay, so now we have improved the model, right? Well, how do you know that? The problem with evaluation is that typically big companies, or really any company, they don't have like a gold standard of query document pairs that we can use to know whether the model is performing correct or not. Doing it manually is also very expensive and slow. So we thought, okay, maybe let's use LLMs to annotate. Okay, this is not very new. But the twist that we gave it is that maybe we should look at only the difference, right? Let's not try to ask the model whether this answer is good or not, but let's just ask the model across many variations of a RAG system, which ones it thinks is better. And we found empirically that it agrees with what human experts will say. When the LLM says this model is better than this other one, the human agrees. So yeah, this is an open source tool as well called Ragilo. If you're interested, check it out to do all of this process. Yeah, just very quickly, the way it works is that you collect the answers from each system separately. Then we ask Ragilo to check, to validate whether a document is relevant or not. Then we use that information to have two answers from two different systems. And it's like a game of chess, right? So we ask the LLM, okay, which one is better? And then based on that, we create an ELO ranking where the top one is the best model that beats everyone else. All right, so at Zeta Alpha, we have a bunch of people that have, most of us have like masters or PhD education, but we are not an experts on every single domain, right? So what we find when we help companies with their use cases is that we need to allow them to create the agents themselves. So for that, the problem is that some people already have built something, for example, in LangChain. So we don't want to tell them, okay, you need to rewrite it in something else. So we need to support the existing thing that they have, but we also have like our own way of doing it, which we think is simpler. You also need to allow them to debug their agent against a version of the real system. And you also want to have some sort of evaluation for them to know which version is better, as well as transitioning to production seamlessly and integrating with standard LLMOps tools for monitoring. So this is the open source project we are releasing this week, which is called RAG Agents, that does all of those things. Let me, in the interest of time, skip this one. You can check out how that works. Yeah, so the point is that, for example, you have this UI where developer can debug their agent and then at the end maybe run against a set of queries and then ask Ragilo to rank all of the variations so that they know which one they might open the PR for. When you want to go to production, then this very simple command gives you a fully working API that you can that integrates also with tracing tools. Okay, so where does that fit in the entire picture? So this is the diagram I showed before. That is in the agent service below. So if you zoom in, the way we want people to work is that they can they have this kind of debugging runtime where they can develop their agents, and they have this feedback loop via Ragilo, but at the same time, they are calling the real APIs, but maybe like a staging index, for example. But then once they are done, it's very easy to just have the same code now just running production in the platform. Okay, so the question is to RAGOps or to not RAGOps. So I think so far I convinced you that implementing RAG in the enterprise takes way more than 5 lines of code. Some of the issues that we need to resolve is that, well, the enterprise has so many use cases, right? So we have to have a system that can handle all of those. So customization is important. Then we want to actually have good results, or like people, like our users are happy using the solution. So you need some way of fine tuning, either the embedding or the retrieval methods and so on. Evaluation is also very important, right? How do you know that this solution is better? Well, you need to have some robust way of evaluating the system. And finally, we need to let the domain experts have a way to easily manage and customize these without intervention from engineering or AI experts. However, if you want to have one takeaway from the talk and you want to still do 5 lines of code for whatever reason, I would say that the minimum you should have is integrate evaluation into your development process. Thank you.
Thank you so much. So we're doing great with time. So if we have any questions, let's jump right into them. Okay, I'll start with a spicy one. I want to ask what's your opinion on one thing that RAG and all of these systems will have in the future that maybe is missing now, and one feature that we've had for so long, but in a few years we'll think it was crazy that we were doing it that way.
I think like reliable agents. Like if you can have reliable agents in a RAG system, it can really allow us to do like some very valuable stuff in the enterprise, especially. Yeah, what was the other question?
One thing that everyone does nowadays, but is kind of insane that it will be deprecated in the future from all RAG systems.
Prompt engineering.
Other questions? Yes.
What is the one thing you think everyone is talking about, but not actually working yet?
Well, for sure, everybody's talking about agents. Whether they are reliable enough to work, to have to be in production, this part I'm not sure. But we should be prepared, right? We should work on this before, and once the technology is there, then we can test it.
So my question is, how is Zeta comparing to Glean?
Well, it's a very difficult question because I don't know what exactly how Glean do their own stuff. But for us, we really specialize more on the search. So we are a bunch of information retrieval experts. So yeah, we really are into like fine-tuning the models and helping our clients get the best answers possible. And also, we have built the entire infrastructure to do our own thing, right? So we can also serve them to be installed on-prem or on SaaS or whatever the situation is.
box for many tasks because we don't know what our customers would use these embedding APIs at their use cases. And also, because of this, we want these embedding APIs can be customized by our customers through simple instructions. And why this is difficult? Before we started work on this, most of the prior research assumed that it is possible to train one retriever on one task, and magically it will generalize to all the different tasks at inference time. We have this beer benchmark, which Nathan, the author, created with us today here. This benchmark has a lot of different tasks, like you want to retrieve evidence for verifying a claim, you want to retrieve answers for a question, and you want to retrieve entities for a from DPP Wikipedia. But most of the people are just training the retrievers on the MS Marco web search log, which is the only available large training data we have at the time, and just tweak the training recipe and hope the quality would improve on all the other inference tasks. And there's some problems. One practical problem is that this search log is just not legally always available to use, especially if we want to put it into our production. And a more fundamental problem is that the assumption that training on one task would generalize to other tasks is not valid. And there is no way for us to customize this retriever once it's trained on a single task. So our solution is, since language models can follow instructions and generalize to new tasks easily, can we bring its capability to the retrievers? And the answer is yes, let's use the data as a bridge. So we do language model to data, then to our retriever through data distillation. And here is the specific recipe that we built. So we start from the web, which has all kinds of web pages. And we prompt a large language model to generate the queries based on each web page. So this is standard query generation task where you generate synthetic queries. Then you can train your retrievers on those synthetic query and passage pairs. But the one thing we made a change here is that before generating the query, we also ask the language model to look at the web page and come up with a instruction or a task, then the query. So looking at a maybe Wikipedia page, the model would generate a task being answer my question based on this web page, and then generates the question is who made the atomic bomb? But if we give it to another web page, maybe a product from Amazon, then our language model will generate a task which is find the production based on the user's description. And the query would be a user description of a product in mind. So in that way, we get all these synthetic tasks or instructions. Then we can train our retriever to read the task and the query together. And this is like Flan. We have diverse enough tasks at training time. So hopefully at inference time, the model will generalize to any new task descriptions or instructions and give the retriever some instruction following capability. So that's one change we made in this recipe. And the other change is that the query we generated from the web page may look good on its own based on the web page, but then it's not good for training the retriever globally. The one difficult about retrievers is that you want to ensure global ranking. You're not just looking at the local relevance. So for example, here the query is who made the atomic bomb, and it's generated based on the web page, which is a character blessed with the power of invention helps human create an atomic bomb. It's a novel or a TV show plot. So the query is relevant to this passage locally, but then if the user asks this question, we would want to show the real history, not this novel or this fiction. That's why we have this global filtering stage where we run the query against our retriever, get a bunch of candidate passages, and run another prompted language model to actually pick the most relevant candidates again. So we get a better positive from the generate synthetic query. So at the end, we get a synthetic instruction, a synthetic query, and a language model mined positive passage that gets us the training triplets that we can use to train our retrievers. So we use this synthetic data and train a standard two-tower dense retrieval. And we combined with some other techniques like pre-fine tuning and some supervised data to boost the performance. And does it work? So this is on the MTAP benchmark, which we have shown many times in this event already. And at the time of publish, the Gecko models are one of the best models on the leaderboard. And specifically on the last row, that zero-shot model is the model trained only on the synthetic data without the final human data that we added. And it's very strong. If you look at the board, I think it's one of the first models that's showing without any supervised human data, without MS Markov bin logs, we can get this high performance. So that's the data. I think we've been talking a lot about superhuman alignment recently. And retrieval has always been a superhuman task because nobody can read all the documents and find the relevant passages. And these synthetic data language model self-improvement is one of the key recipes that we help us achieve the goal. But besides data, we also need good architectures to digest the data. And I think a lot of the problems or difficulties we have with training smart retrievers is because of the dense two-tower model architecture that we are trying to encode everything into a single small vector before seeing the real query. And that's why the model doesn't generalize, cannot do reasoning, and a lot of amazing things. So actually, at the spectrum of the retriever, on one end, we have this very fast two-tower model, but they are trying to condense everything into a single embedding, which hurts the generalization ability and all the emerging capabilities we see with language models. On the other hand, we have the cross-attention model, which is slow, but you just put your document and your query into the context and ask the model to encode them all together and answer the question. And retrieval is always a game between, it's always a trade-off in efficiency and quality. So there is this multi-vector retrieval line of research that kind of want to find the balanced sweet spot in the spectrum. And one of the very famous model is Cobert. Because of the time, I won't go into the details of our work, but basically there's some fundamental limitations in Cobert that is causing a training testing mismatch. And in our work, XTR, we solved that mismatch. And we have another multi-vector retrieval model that is way more faster, and the performance, the quality is great. And I think the main takeaway we learned from this research is that actually when we train XTR, this multi-vector retrieval model, which is something between dense vectors, dense two-tower models and cross-attention models, we don't have to use all those synthetic data we built before in the first part of the talk. We just trained on MS Markov, but we're seeing much better generalization ability of this model than our two-tower models, which shows that actually if your architecture is representative enough, you don't have to do a lot of the hard tricks you have to do with the dense two-tower models. And that brings us to the next question. If we don't have all these efficiency limitations, and if we can just put the entire Wikipedia into the transformers context, what would happen? And this year, I think this is the time it's ready to start this research. This year, we are seeing a rapid growing of the context window of large language models. At the beginning of the year, we have Gemini and a lot of the models whose context windows are at most 32K. But in a few months, we're seeing GPT-4 goes to 128K, Cloud goes to 200K tokens, and then Gemini 1.5 Pro supports 1 million token in its Cloud API. And in our research stack, this actually, we can scale it up to 10 million token. And what does 10 million token mean? It means 1 hour video or 11 hours of audios. It means over 30,000 lines of code, which is a medium-sized code repository size. And it's over 700,000 words, which is about a few thousand to 10,000 of documents that you can put directly into the context window. And with that, we are seeing a long context paradigm shift. Previously, to deal with those very long information, very long context, or a lot of the knowledge, that's why we have to build specialized tools or RAG systems to handle them. To digest documents, we have to build retrievers. To digest tables and
tables, very large tables, we have to build SQL or databases. And then we have this Lagrange model doing iterative tool calls to use them. And there's cascading errors from every stage to the other stage. But now with this long context window, we can put medium-sized corpus directly to the long context and prompt a model to answer the question. And then we can do all of the like SFT, RAHF directly on this very simple prompt-based models. It simplifies a lot of things for model developers, and for our users, it's even better. Like we don't need to build a RAG system. We just need to prompt our model as how we prompt GPT or Gemini now. So now I would say the 1 million token length is a system change. We know our system support it. We can run inference at a reasonable speed, but we don't know the quality. We don't know whether putting 1 million token into the model and it can just do retrieval well. So that's why we do this research, which is the LLOPS benchmark, where we build a benchmark to test can language models subsume retrieval, RAG, and SQL tasks. Before this work, most of the evaluations for long context models are needle in the haystack, which is a very synthetic evaluation task that you have some text from the web and you insert a synthetic piece of text, which is your needle, and you ask your model to find that needle. This is very far away from the actual retrieval task we're seeing, where you need to understand the semantics of the query, you want to reason over your document and give the answers. And besides that, these benchmarks have some other limitations, like they're not really the long context. I think when we write the paper in March this year, most of the existing other benchmarks are often shorter than 100K tokens, which are not actually evaluating the 1 million context capability of our models. And because their lengths are fixed, they have a fixed expire date. Like as our models grow bigger and bigger in context lengths, this data set would get expired. So that's why we created this LLOPS, Long Context Frontier Benchmark. And it contains 6 tasks and 35 datasets across retrieval, RAG, SQL, which is a compositional reasoning task, and multimodal tasks. And specifically, we have single hop, multi-hop, single needle, multi-needle task, retrieval, and RAG tasks. We have some image and audio retrieval tasks. We have SQL, which is interesting. Basically, we're putting the entire table into the context. And instead of asking ask a model a natural language query, like how many of the employees are over the age of 35 whose salary are below 5,000. And the model would, the system would previously do semantic parsing and then execute that SQL query in a database. But now we just want the model to output the final answer and do its computation internally inside the transformer. And we have many shot ICL, which is we put the entire training set into the context and see if the model can just learn the task by this many shot context. I think one interesting thing is the prompt that we built for retrieval, which is a instruction at the bottom, at the top saying you want to retrieve the passage given the query. And then we have all the passages concatenated just in text in the prompt, starting from ID 0 to ID 1000. And we provide a few short examples to show how this task looks like. And then we give a new query and ask the model to generate the final answer, which is a document ID. And if you look at this, because we can do prefix caching with these autoregressive models now, this is not as slow as we thought. Even if we have 1 million tokens in the context, which consists of thousands of passages, the whole encoding can be cached. And that's like building a retrieval index. And at inference time, you just load the cache into your GPU or TPU and do the only encode the query again and do the decoding of the IDs, which actually makes this a lot faster. So now let's look at the quality. We compare 3 API-based models at the time, which are the state-of-the-art long context models. First is Gemini 1.5 Pro, and we have GPT-4o. We found it's better than the other GPT models on long context tasks. And then we have the Cloud 3 Opus model, which supports 200K tokens. Among these models, what we're seeing is that Gemini performs very well on all of the tasks. And I think it's followed by GPT 4.0. But the more amazing thing we're seeing is that we have all these specialized systems, which are retriever models, RAG models, and SQL databases as the baseline. And compared to this, these long context models are doing actually a very good job. On retrieval task, Gemini is not worse than Gecko, which is the first model that I described in this talk, that we spend so many efforts trying to get data and build it. But Gemini, without any fine-tuning on this retrieval task, can just do very well through prompting. Similarly for RAG, and on these multimodal tasks, Gemini is already better than our fine-tuned multimodal retrieval models, because I think the Gemini developers just spend a lot of time training the multimodal together with the text, so it's actually has much better generalization ability. And we're looking at how these models scale with longer context lengths. Do we still have all those lost in the middle problems with longer context? The answer is yes. The context, once this context gets longer, the model's performance drops a little bit, which means the models are still suffering from reasoning from longer context. But that also happens to all these specialized baselines. Like when we use a retrieval model, like a Douwe encoder, if you give it more passages, it also suffers from the same problem. So I would say this is not a bad news. And if you look at the curves, the Gemini model is often above or similar to these specialized models across different context lengths, which is still a promising result. So to summarize the talk, can we just let language models do retrieval? I would say based on our evaluation on the Loft benchmark, the training gap isn't that a problem. These models are just trained on next token generation, but then out of the box, long context models already do very well on these retrieval and RAG tasks. And I think there's a lot of modeling works we can continue doing to make it become even better. The most simple thing would be just add this data to the fine-tuning set of Gemini. And about the computational prohibitive things, I think long context model is great because it supports all this instruction following and reasoning capabilities. And I really think that's the architecture we should go in the future. And we have a lot of expertise in from retrieval background to make things work faster. Like we can cache these embeddings, we can do near approximate search over these embeddings instead of doing brute force computation. And a lot of things we've built for covert XTR multi-vector retrieval can be brought here to make these architectures go even faster. And finally, as I said, I think retrieval is always a superhuman task, and all these synthetic data generation recipes we've made will keep making these long context models be better at our tasks. Yeah, so thank you.
Zhuyun, I think it was a really nice talk. Do we have any questions? Yes.
I really like your talk, and I think this is first time I'm seeing someone hitting the right point. So my question here is, so as you said towards the end of your slide that for long context, you see the performance is degrading. What do you think is it at the embedded space geometrically, what is happening? And kind of to piggyback on that, I mean, first of all, what is a context geometrically in the embedded space?
We haven't checked the space of the embeddings of those tokens, but I think one thing we noticed is these models still have a lost in the end behavior. Like they pay more attention to the start of the context. And when you concatenate all of the passages together, they pay more attention to the first few passages instead of the last ones, and that gives them a bias.
So I'll just kind of give what is my understanding. So in my understanding, a context is a hyperplane that is projected by any neuron. Because if you see the affine function of a feed-forward neuron, that's a straight line if you see in the 2 dimension, but that's a hyperplane. And the activation function is just an index of the distance of the point relative to that hyperplane. So when you have long context, you put more hyperplanes in this because you are trying to find a subspace in the general space. That's the length of the tokens. Each token is representing a context space, okay? And you're creating a subspace. And when you put, let's say in this room, correct? You can find the subspace with 4 walls. But if you put a long context, put many more walls, you'll create more corner regions where there will be confusion. And that's in my view, is causing the degradation in the performance. So it's really not long context, it should be relevant context. I mean, you are right that long contexts are not always the answer. Sometimes you will need a long context. What is really happening is you have a hyperdimensional space where you are using hyperpolygons to approximate any generalized hyper shape in the space, geometrical embedding space.
That's a very interesting perspective. I think we should talk this offline. Yeah.
Yeah, thank you. So once again, thank you, Zhuyun, for your talk. And yeah, one more round of applause, please.
Thank you.
Yeah, so this concludes our kind of presentation setup, and we'll move on to the final part, which is a panel with all of the speakers that are still here. So yeah, I invite everyone that was here before to stand up again. We have a few mics, only 3 chairs, so if you don't mind standing for some people. Yep. Don't be shy, you have been here before. Yeah, so please have a seat. You want to join us as well? Oh, right. So in this panel, we kind of have to wrap up this whole Transformers at Work workshop. So first, I will start with a question that has been on my mind based on all of the talks that you gave today. Then we can also have some questions from the audience if you have time. So yeah, let's ask a question maybe to anyone that wants to volunteer. Maybe to Natalia, it's more relevant. I have this feeling that we're kind of in a race against scaling the models versus finding more ways to make them more efficient. Which do you think is going to be the winner in the near future? Is it can we keep going for long, or do we have to start thinking about efficiency more?
I think we definitely need to start thinking about efficiency more because, yes, our chips are really big, but still it takes months to train very large models. So we should train more efficient models. And I think, like that you addressed this question to me. I believe that, and that related also, I think, to the comment by Douwe earlier, that the fact that transformers are successful is because they have been designed for GPUs. And I think this hardware, software, algorithm co-design will become essential. And I think there is an opportunity with our chip, but not necessarily with our chip. I think we need all to think more creatively and to come up with new approaches to training and think which hardware will be the best fit for that. And it's a closed loop iteration because we won't survive just chasing very large scale models moving forward. We will burn all energy on planet Earth.
Anyone else want to volunteer?
Why are they mutually exclusive? So I think if you want to train a bigger model and you can do it more efficiently, then you have to spend less money, or you can train an even bigger model. So yeah, I think we should be doing both.
I agree, but my kind of view is that right now one of the two is winning. So at some point you have to bring them both up to the same speed where they're co-developing at the same pace.
Which one is winning?
I would say scaling.
I don't think so. I think if you actually look at what's happening with sort of prices coming down and like alternative hardware providers and things like that, I think most of the investment is happening on the efficiency side right now. So
great, thank you. Any other views?
Yep. Hi. So I had a question about mostly about training data. I feel like all of these models require training data to make them sort of what they are, state of the art. So in general, what are your thoughts on training data? Do you rely on humans to generate them, or are you more leaning towards synthetic generation of such training data? And what are your thoughts on that? So just curious.
I can start. I think my thoughts is like you need to make sure quality of the data. So like if you have ways to characterize the quality of your data, so you have a good way of handling the task. So and that's the first thing to have. Like, is it a human generated data, synthetic generated data? Is like the same rules about like how you assess the quality. Human generated data can be crappy same way as synthetically generated data, but synthetically generated data is like much cheaper to do. And if you have the ways to generate the synthetic data for the new tasks, you're probably going to go faster with all of these ideas.
Yeah, I think we'll see more and more synthetically generated data moving forward. That's my opinion.
Can I maybe just like think out loud with you for a moment here? So these are like half-baked thoughts, but I feel like the story of the last couple of years has been a huge focus on post-training, right? Lots of fine-tuning and manual data collection, partly because we're in a performance race between companies who are at the frontier to deliver things directly to customers. But if we like take a step back and just like think about the research question, then the thing that led to the current breakthrough was actually people like making unsupervised learning work better and us being able to leverage like unlabeled data better. And like, you know, the pioneers of the field have been saying this forever. Like Jeff Hinton gives this talk where he talks about, you know, reinforcement learning compared to supervised learning versus unsupervised, and says how many bits of information might there be in the adult human brain? And to acquire enough information by age 30, you're probably consuming 10,000 bits per second. It's clearly not RL or supervision that's giving you that information. Or Jan LeCun has the famous like cake analogy of like the cake, the icing, and then the, you know, reinforcement learning being the cherry. Like all the attention is focused to the icing because it gives us short-term gains. But I suspect if we're going to continue to get really big breakthroughs, it'll still be coming from better ways of doing unsupervised learning. But half-baked thoughts.
Yeah, another thought here is that as our tasks become more difficult, it's really harder and harder to get high-quality human data. Like, say, building an agent, it's very expensive to ask the human to write step-by-step agent execution traces. And our raters are usually very lazy, and they just want to spend more time and earn more money. So I think if we have the fixed set of budgets, we would think how we can use this to ensure we get high-quality data at the end. Should we just ask raters to write the data, or we get synthetic data and then build a very good synthetic data critic model with some human labels at the end to make sure we get much larger high-quality synthetic data?
One more half-baked thought in. So since I'm putting half-baked thoughts out there, which is just one other place where maybe synthetic data is easier to do is places where verification is more straightforward. So code and maths and things where you can like formally verify the data feel to me like places where synthetic data generation will happen very quickly or be much easier to do. And we are seeing this already in the places where the models are accelerating.
Lots of good takes. Let's go on to your question.
So I'm curious to hear your thoughts on how surprised you guys are on the fact that OpenAI released a model that does inference time optimization, kind of. And do you guys see this as a paradigm shift versus what has been happening before?
Yeah, I think when Chain of Thought came out, this was sort of an obvious next thing to try to do, is to try to train on sort of the rollouts of the chains. The way they do it obviously is a little bit more intricate because of sort of the RL algorithms that they're using to do it. But I think in like old school machine learning pre-transformers, we already knew that there was a lot of test time optimization you can do. We would just be doing sort of KNN style search or things like that during test time as well. So I don't think it's a new paradigm in that sense. I think it's just sort of a, yeah, sort of obvious next step maybe.
Yeah, maybe one thing is that, so before, I guess you will do like chain of thought manually, or like you have to do it in your own code. But now if it's integrated, there's also maybe not a way to opt out, right? So now you need to spend the tokens for it to do it, even if it's like maybe a simple task. So yeah, maybe it's a new thing, but does it fit, does it solve all of the use cases nowadays, or is it just another thing that you might go to for specific ones?
Maybe just one sentence to add that surprised not. What's interesting to observe is if we will see, and it looks like we will see similar scaling law for inference time as we've been seeing for training. So it's been shown that you have this power law. If you increase exponentially the compute, you improve the performance linearly. And it looks like it's also applicable to test time, which was for me surprising.
So we're here to talk about transformers at work, right? So in applications, in real companies, in the last year or 2 years, we've really seen sort of the large models and the frontier pushes with super large compute investments being kind of stealing the show. I thought a really interesting thing was that Satya Nadella, when launching the sort of latest Copilot thing, said, well, actually, the whole LLM layer is commoditized now with Llama and other QN and all these models. I'm curious what you guys think, whether he's right that actually the application layer of really solving business problems is going to be the next frontier, rather than just the scaling law and continuing that.
Yeah, I very much agree with that. I think language models are in a way a solved problem. So I think I even said that in my talk. Yeah, so the hard problem is how do you contextualize the language model properly, right? So it's really about the entire system. If you actually look at a real world deployment with like a large bank or something, that's a giant system, and the language model is like, I don't know, 10% of that system. You need to get all of this other stuff right. Otherwise, the language model can't do its job, right? Like if you can't extract the information the right way or do retrieval the right way or re-ranking or all the other stuff that you have to do to make sure you give it the right information, or then the post-processing that you need to do, then you're useless, right? So for solving real problems, we should be thinking about systems, not models. And thinking about how to optimize those systems. So things like DSPy are great examples of that too, I think.
Yeah, I wanted to add also that you could see that large language models are really good as, so I call it creative tasks. So where like I'm fine with them going to, let's say 95% accuracy, if like I would make this paradigm. But getting to another 5% is really hard. And that's what's the most important part for us to get there. So like where you actually measure the quality of like how precise those are. And that's a really hard problem. Like it's much easier to go to 95% than the next 5. Yeah, that's gonna be the next breakthrough, how you actually make those models make actions and also reliably. We are not there.
Yeah, I'm in agreement completely with the idea of systems rather than models. I think the human efforts of like a machine learning engineer should go into designing the system and figuring out where the LLM fits in, rather than just scaling up a larger model. And I think that the two things can work well together. Like we can get larger models that work better in our systems, but I think leaving the optimization of the language models to a couple of the really well-resourced groups to make this all open source, and then focusing the dev efforts on how we can actually apply them and how we should string these together and optimize that. That's where I'm excited.
I'm taking an opposite view. Like, I don't think language model is a solved problem. There's so many capabilities that are still not there, and it cannot be elicited just through inference time techniques. Specifically, when building agent, we were spending a lot of time prompting, but our model can do like a 3-turn, 4-turn task, but it cannot behave like you're hiring someone and who grew with your team, pick up the task, and in a half year, it becomes a very capable software engineer. We're not seeing that. And I just don't think that can be done through inference time COTs. Similarly, the SQL task that we tested in the lab benchmark, we give it a table, ask it to compute everything inside the transformer. I think it's just far away from getting that task done. So,
but that's a systems problem, not a model.
isn't it both?
Yeah, so I think what I was saying, that's a systems problem, like solving the big thing, right? So I think like why O1 is interesting, back to that question, is that you're compressing a lot of this kind of system stuff inside the language model. Your talk was also about this, right? So the ability to retrieve on the fly and things like that, but then making that a part of the model. So I think when I say language models are a solved problem, it's more like predicting the next word, sort of like that. We're pretty good at that these days, right? So, but there's a lot of this other stuff around like taking actions and things that we still have to learn, yeah.
Oh yeah, it's less exciting now because I don't disagree with you anymore. Or I would maybe just say, so like insofar as language models are solved, like literally language models are solved, yes, but I don't think we figured out well really how to train these things on like truly multimodal data. And I do assume that even on the language tasks, we'll see performance improvements if we can correlate across different modalities. And then yes, I feel like increasingly the things that are currently put into systems will end up in the models. And I don't think the models are reliable enough that like just like I don't like often systems are helping us take unreliable parts and use them in reliable ways. But I don't think the current generation models is reliable enough that even if we do that, we'll get good agents. I do think we need better models.
Great discussion. So just to wrap things up, since we're almost out of time, I would want to ask everyone kind of a more prediction side on where do you think AI will be in just 1 year from now?
We'll have AGI. No, just kidding.
Do you not have it already?
Have you changed your voice on purpose, like to be scary? I hope that we will be in a point where they can help us to actually run our chores. That's what I was hoping for. So like I don't have to be on top of my to-do list about like all the chores part and focus on my work. And also like they can do actions reliably. So they actually release my stress from being on top of paying my bills and things like that, and all this other not so interesting stuff. And I can focus just on exciting creative tasks. I'm done.
My turn. Okay. I think maybe from the more technical and how concept, I think that we will see switch to MOEs, and most of the most popular models will be MOE because they're more compute efficient. We will see a lot of multimodal and learning from multiple modalities, and also an ability to deal with much longer contexts. So right now we're talking about all of those directions as promising, and yes, the field is developing really fast, but still it takes time to like figure out how to merge all that together and make it useful. So boring predictions.
I think I have like a more pessimistic view. So what I would like is the next year there is actual like a big gap in improvements, because I feel like if you look at I went from GPT like DaVinci 3 to 4, it's like quite a large improvement, but I don't feel like these days most are improving that fast. So, and I feel like the speed is necessary for enterprises to continue pushing and trying to adopt Gen AI for actual valuable applications.
Yeah, so I think 2023 was the year for building cute AI demos in frameworks and then sort of showing people what would be possible. I think this year is really very much about trying to productionize the technology. We're starting to see more and more of that, but probably not as much as we would have liked to see or expected to see. I think next year is going to be the crunch year for AI, where we need to show ROI. Right, we're investing a lot of money and time as a whole, like society, into this technology, and yeah, we need to show that that was a good investment. So that's really what next year is going to be about. And based on that, there are a couple of very different futures.
Yeah, trying to think about this with just a one-year time horizon is tricky. A lot of these things are spiky as well, like big model training runs and new research breakthroughs. I actually feel like we've kind of been sort of frogs in water even across the last 2 years. Like people constantly say like, oh, we haven't seen like a big moment like GPT-4 from Text DaVinci 3 to 4 since then. But we have actually seen like pretty continuous improvement in all of these systems slowly over time in such a way that you have been acclimatized to it rather than it being, oh, wow, this is like suddenly better. And I also think that we're probably going to enter a period of frustration where the models seem to have gotten a lot better, and yet we're not seeing the ROI from them. So like we had, you know, when O1 came out this week, like Terence Tao said, he thinks this thing operates at the level of like a grad student mathematician. So like, there's a weird paradox where at the same time people who I respect are saying, hey, I'm using this model and I'm seeing like real utility from it. And also no one is able to see like any economic uplift yet that they can point to. And I think part of the problem is that if I gave you like an army of cheap, smart people, you would have to re-architect your life somewhat to like see any benefit. Like I recently started working part-time with an executive assistant, and it's really hard to actually like use that person well. I have to change the way I work. And that person is definitely AGI, right? Like they're a smart, like general purpose, intelligent thing, like they're human that I interact with mostly via my computer. But getting value from them, like getting tangible ROI is still difficult. So I don't think that just because we've like not yet seen the ROI means that we're not going to get it. I also don't think it means we haven't got very smart systems or the systems haven't improved. So I think next year probably we'll have lots of people saying nothing's gotten better, nothing's gotten better, nothing's gotten better, because we're going to have to re-architect a lot of the way we do things before we'll see the value.
I think I have two takes. One really quick because we've already kind of covered it, but I do see systems as a big next step, especially I think people will be on board with the idea of building AI systems rather than models. I think O1 is already a system, ChatGPT is a system. I think people will see it that way, that chaining these calls together is a good idea. And then unrelated, but I think on-device AI and also personalization is going to be a big thing. So I think, especially if you're talking like assistants like ChatGPT and you're talking about on device, I think it's going to know your data, know you, and interact with you as the user. So I think that's the next step for these sort of LLM assistants. And then I think like on device LoRa adapters, the Apple Intelligence stuff, I think that's pretty cool too. So on device systems and adapting to your use cases on private and edge computing there. So that's my take.
So in the long term, I want AI to be to have consciousness, to be self-conscious, to just like a human, like my friend, like my colleague. And I think go into the next year, that is memory. I want to see more development on memory, and that goes to personalization or adapting to a very hard task through learning it for maybe 2 to 3 months, things like that, self-reflection. So I really want to see more research on that time. I think long context is giving us some starting points to work on that, but then just having every token in the context is not the memory that I'm looking for.
Can I add one more? I agree with everything that was said, and I think one piece is missing is also cost reduction, and that's tightly connected to ROI, because I think one of the reasons why it's not economically viable today, because it's still very expensive to run that. So.
All right, so it's 6 o'clock. Let's wrap this up. Let's give another big thank you for all our fantastic speakers, the real transformers at work. And don't leave just yet. We have food, we have drinks, and the musicians are just dropping in. They'll be setting up and getting us into the weekend with some really good Berkeley, jazzy, soulful, funky vibes. Honey Knuckles. Yeah, with that, we're closing this part. There are many questions remaining, but we can handle those over drinks, music, and some evening sun in the Berkeley area. Thanks.
Thank you. Thank you for organizing this.
Gift for all of you, sorry. There you go. Thank you, gift for all of you.
Thank you.
Thank you. I just wanna thank my boy Miles. If it weren't for him, I wouldn't be here. And even though it's taken a while, thanks to all those who have appeared. Saya and yes, Fred Tackett, Charlie Tuna and Cookie. I just wanna thank my boy New. Cause New is the one who came through again. I also want to thank B+, always there for me when I'm in a clutch. And thanks to all who didn't let me fall. To you, love, loves all of you.